Hello there, and welcome to Sleepy Science Vault. Everything you think you know about the world rests on a single, quiet assumption. That the things around you are real. That the chair beneath you, the ceiling above you, the darkness just outside the window, that all of it actually exists, independent of you, waiting patiently whether you look at it or not. It seems obvious. It feels certain. And yet, the moment you begin to pull at that thread, the whole picture becomes something far more strange and far more beautiful than you might expect. Reality, at its simplest, is usually defined as what actually exists. What is truly there? What is not imagined, not constructed, not dependent on any one mind to perceive it? That's the working definition most of us carry through our days without ever needing to examine it. And for ordinary life, it works perfectly well. But here's what's interesting. Across every civilization that has ever existed, across every culture, every religion, every philosophical tradition, human beings have described reality differently. The ancient Greeks debated whether the world was made of water, or fire, or pure mathematical form. Indigenous traditions across the world speak of reality as layered, animated, deeply relational, not a backdrop, but a living presence. Modern physics describes it in terms of fields and probabilities and dimensions we cannot see. In religious frameworks the world over point to something beyond the physical entirely, something that underlies all visible things. None of these views are simply wrong. They are each, in their own way, attempts to answer the same impossible question. What is this place? What is all of this? In our daily lives, of course, we don't dwell on that question. We move through the world assuming it is solid, stable, consistent. The floor holds. The sun rises. Objects stay where we leave them. This assumption is so deep, so thoroughly baked into our experience, that we barely notice we're making it. Reality, for most of us most of the time, is simply whatever is in front of us. But here is something worth sitting with. Your senses do not show you reality directly. Not even close. What your eyes detect is electromagnetic radiation, light, bouncing off surfaces. Your brain then takes that raw signal, combines it with memory, expectation, context, and prior experience, and constructs an image. What you see is not the world. It is your brain's best interpretation of the world. A model. A rendering. And the same is true for every other sense you have. What feels real to you, right now, in this moment, that feeling is partly coming from something outside you and partly being assembled inside you. The two are inseparable. You have never experienced raw reality. Nobody has. Every experience of the world is already, always, a collaboration between what is out there and what your mind brings to it. This doesn't mean the world isn't real. It means the relationship between you and reality is far more intimate than it appears. Science, of course, has its own answer. From a scientific standpoint, reality is matter and energy, operating according to laws. Physical laws. Mathematical relationships that hold everywhere, for everyone, at all times. Electrons behave the same on the other side of the universe as they do in your body right now. Gravity doesn't take days off. In this view, reality is impersonal, consistent, and knowable, at least in principle, through careful observation and experiment. It's a profoundly powerful framework. And yet, even within science, cracks appear when you look closely enough. Some physicists and philosophers have begun to argue that consciousness itself may be more fundamental than matter. Not a product of the brain, not an accident of evolution, but something deeper, something the universe may be built from, or built toward. This is not a fringe idea. It is taken seriously by serious thinkers. And it changes everything about what we mean when we say the word real. Others take a different and perhaps even stranger path. They suggest that what reality is, at its most basic level, is not matter and it's not consciousness either. It's information. Pure, abstract, mathematical information. In this view, the physical world is almost like a kind of output, a display, of something more fundamental happening beneath it. The universe is a vast computational process, generating experience the way a program generates images on a screen. Which naturally leads somewhere most people find deeply unsettling, or deeply fascinating, depending on their temperament. The simulation hypothesis. The idea that what we call reality could be a constructed environment, something running inside a system we have no access to, created by minds or processes entirely beyond our understanding. It sounds like science fiction. But some of the most careful philosophers of mind and theoretical physicists have noted that we currently have no way to rule it out. Not one. And perhaps that, more than anything else, is the most honest thing that can be said about reality at this particular moment in human history. Our understanding is incomplete. Not slightly incomplete. Not almost there. Genuinely, profoundly, beautifully incomplete. We have mapped the surface of other planets. We have sequenced the human genome. We have built machines that can process more information in a second than a human mind could in a lifetime. And still, the simplest question, what is real, remains open. Not because we haven't tried hard enough, but because the question itself seems to deepen every time we think we've reached the bottom of it. And there is something quietly wonderful about that. Something worth resting in, especially now, in the late hours, when the world is still and the usual noise has faded. The question isn't solved. It may never be. But it belongs to you just as much as it belongs to any philosopher, any physicist, any ancient sage who ever looked up at the sky and felt the enormity of not knowing. Reality is the thing we've always lived inside of, and the thing we've never quite been able to hold. There's a useful way to think about reality that doesn't require any equations, any ancient texts, or any particularly deep philosophical training. It simply requires noticing that not everything we call real is real in the same way. When you feel a sharp pain in your hand, that pain is real. No one can feel it but you. No agreement between people created it, and no scientific instrument can measure exactly what it is like from the inside. It belongs entirely to your experience, your body, your moment. That is one kind of reality. When two people shake hands and one of them becomes the other's employer, something real has happened. A relationship now exists. An obligation. A set of expectations with genuine consequences. And yet if you scan that handshake with every instrument science has, you would not find the employment contract hiding somewhere in the molecules. It exists because both people and the society around them agree that it exists. That is a different kind of reality entirely. And then there is the world that was here long before any human being arrived to perceive it, name it, or argue about it. The tectonic plates grinding slowly beneath the ocean floor. The light from distant stars crossing billions of years of empty space. The chemical processes happening inside a seed buried under winter soil, waiting for warmth it cannot think about or hope for. That world does not depend on anyone's experience, and it does not depend on anyone's agreement. It simply is. That is a third kind of reality. Philosophers and cognitive scientists often describe these as three distinct layers. Individual reality, social reality, and independent reality. And understanding the difference between them quietly changes the way you see almost everything. Individual reality is the world as experienced from the inside. It is your perception, your memory, your emotional life, your sense of who you are and what the day felt like. It is entirely real, and at the same time entirely private. No one else has ever had access to your experience. No one ever will. The particular shade of meaning that a certain song carries for you, the specific quality of how a childhood memory feels when it surfaces late at night, these are as real as anything in the universe, and yet they exist nowhere but within you. Social reality is the vast invisible architecture that human beings have built together over thousands of years. Language itself is social reality. The meaning of words is not written into the fabric of the universe. It was agreed upon, slowly, collectively, across generations. Money is social reality. A $20 bill has no more intrinsic value than a rectangle of paper with ink on it. Its value exists entirely in shared belief, in a collective agreement so widespread and so reinforced that it feels indistinguishable from physical fact. Countries are social reality. Borders are lines that exist in law and in minds, not etched into the ground by nature. Marriages are social reality. Crimes are social reality. Reputations, ranks, titles, rules, all of it held in place by a web of human agreement so dense and so old that most of us never see it as constructed at all. And this is worth pausing on, because social reality is enormously powerful. It shapes lives. It starts wars. It determines who gets resources and who goes without. Just because something is socially constructed does not mean it is weak, or unimportant, or easy to change. Some of the most immovable forces in human life are forces that exist entirely because people believe in them together. Independent reality is what remains when you strip away every perceiver and every agreement. The laws of physics. The age of the universe. The atomic weight of carbon. These things were true before there was anyone to discover them, and they will be true long after. Independent reality is the bedrock. The non-negotiable. the part of existence that doesn't care about our categories or our feelings or our civilizations. And here is what becomes genuinely interesting when you hold all three layers in mind at once. Most of what we call the world is a layered mixture of all three. The chair you're sitting in is physically real, independent reality. But whether it's furniture, or property, or an antique, or trash, that depends on context, culture, and agreement. And how it makes you feel, what memories it carries, whether it feels comfortable or foreign, that's yours alone. We are almost never dealing with just one layer of reality at a time. We are always navigating all three simultaneously, usually without noticing. There's another way of thinking about this that some traditions find more satisfying than any layered model. The idea that reality is not meaningfully divided into separate layers at all, but is fundamentally one interconnected whole. That the boundaries we draw between self and world, between individual and society, between observer and observed, these are useful fictions, not true divisions. What we call individual reality and independent reality aren't two things that interact. They are expressions of a single underlying process that we have no name for and perhaps no instrument capable of measuring. This view appears in different forms across different traditions. In certain schools of Eastern philosophy, in some interpretations of quantum mechanics, in ecological thinking, in systems theory. The details vary enormously. But the underlying intuition is similar. The universe is not a collection of separate objects. It is a web of relationships so entangled that separating out the pieces is always, to some degree, an act of violence against the truth. Now, before we go any further, it's worth making a distinction that sounds simple but turns out to be surprisingly slippery. Existence and reality are not always the same thing. Consider a pain that is so severe it fundamentally alters a person's life, but which no medical test can detect. Does that pain exist? The person experiencing it would say, with total certainty, yes. Does it exist in the same sense that a broken bone exists? That's less clear. We might say the pain is real but its cause remains unknown, or that it is real in the individual layer but not yet locatable in the independent layer. The language starts to strain. Or consider a character from a story. Sherlock Holmes does not exist in the physical world. There is no one at 221B, Baker Street. And yet Sherlock Holmes is not nothing. He influences real behavior. People travel to a real address in London because of him. Academics write careful papers about his methods. He exists somewhere, in imagination, in culture, in language, but not in the way a person exists. Or consider a number. The number 7. Does it exist? It doesn't take up space. You can't trip over it. But without it, nothing in mathematics works. Without mathematics, nothing in science works. Without science, none of the technology that shapes modern life would be possible. 7 is not nothing. But what kind of something is it? These aren't merely academic puzzles. They point to something genuinely unresolved at the center of how we understand the world. Existence comes in kinds. Reality comes in degrees. and the boundaries between what is real and what merely exists, between what exists and what is imagined, between what is imagined and what is, in some sense, more true than either. These boundaries are softer than they appear. And now we arrive at something that most people sense, in quiet moments, but rarely think through all the way. You have never experienced reality directly. Not once. Not even for a moment. This isn't a criticism. It isn't a spiritual claim or a reason to despair. It is simply how the mind works, and once you understand it, the world becomes a richer and stranger place. Your brain is not a passive recorder. It doesn't sit back and let the world stream in. It is an active, relentless prediction machine, constantly generating its best guess about what is happening outside your skull, and then checking that guess against incoming sensory information, and updating. Always updating. The experience you are having right now, the sense of a room, a surface, a temperature, a sound, a self sitting in a particular place, is not raw input. It is the output of an extraordinarily complex modeling process that has been running since before you were born. This is not a metaphor. Neuroscientists now widely describe perception as a form of controlled hallucination. The brain generates a model of the world. Sensory data flows in and either confirms the model or forces a small correction. What you experience is the model, not the world itself. Never the world itself. The philosopher Immanuel Kant arrived at a similar conclusion through pure reasoning, more than 2 centuries before modern neuroscience existed. Kant drew a distinction between what he called the phenomenal world, the world as it appears to us, and the noumenal world, which he called the thing in itself. The thing as it actually is, independent of any mind perceiving it. His argument was careful and precise. Everything we experience comes to us already shaped by the structures of our minds. Space, time, causation. These aren't features we discover out there in the world. They are frameworks our minds impose on experience in order to make sense of it. We cannot step outside those frameworks. We cannot take off the lens of human cognition and look at reality bare. The thing in itself, whatever it truly is permanently beyond our reach. This was a radical idea when Kant proposed it. It still is. Because it means that the entire edifice of human knowledge, every experiment, every observation, every measurement, is built on perceptions that are already, from the very beginning, shaped by the instrument doing the perceiving. We are not looking at the universe from outside it. We are part of it, and our way of seeing is inseparable from what we see. Neuroscience has since found this same truth written into the physical structure of the brain itself. There is a remarkable experiment that illustrates it clearly. Researchers presented people with a simple task: press a button when a light flashes. Straightforward enough. But when the timing was measured precisely, something strange emerged. People consistently reported experiencing the flash in their own button press as happening at the same moment, even when there was a measurable gap between them. Their brains had quietly adjusted the timeline, stitching the 2 events together into a single seamless experience of simultaneity. The brain does this constantly. It receives sensory information at different speeds from different parts of the body, A signal from your fingertip travels a different distance than a signal from your ear, and it smooths all of that out into a coherent, unified moment that feels instantaneous. The now you experience is not actually now. It is a very slightly delayed, carefully edited, beautifully assembled version of now. And the editing goes further than timing. The brain rearranges sensory information in ways that serve comprehension. Visual information from your two eyes arrives separately and is stitched into a single image. The blind spot in each eye, the place where the optic nerve connects and no photoreceptors exist, is seamlessly filled in, so completely that most people live their entire lives without ever noticing that a piece of their visual field is, in a literal sense, made up. Sound is processed and matched against learned patterns so quickly that by the time you consciously hear a word, your brain has already predicted what word was likely to come and has partially generated its meaning. You are not receiving the world. You are receiving your brain's best current story about the world. And most of the time, that story is good enough. Remarkably good, in fact. The fact that human beings can build bridges and write symphonies and navigate city streets and recognize the faces of people they haven't seen in decades, all of this is a testament to how extraordinarily well this predictive system works. But it is a story, a model, a representation. And there is something quietly liberating about knowing that. Because it means that the rigid, solid, fixed world that sometimes feels so overwhelming and so immovable is, in some sense, less fixed than it appears. The mind that generates your experience of the world is not a passive victim of it. It is a co-creator. It brings something to every moment. It shapes what it sees even as it is shaped by what it sees. The layers of reality, individual, social, independent, and the fact that we access none of them directly, always only through the interpretive lens of a mind embedded in a body, embedded in a culture, embedded in a universe it did not choose and cannot fully see. All of this points toward the same quiet conclusion. The relationship between you and reality is not simple, and it never was. It is intimate. It is collaborative. It is, in the deepest sense, a relationship, something ongoing, mutual, never quite finished. And perhaps the most honest and most peaceful thing to rest in, as the night settles and the mind begins to slow, is the knowledge that you don't have to have it figured out. No one does. The greatest minds in human history didn't. And somehow, despite that, here we all are, experiencing something, sensing something, reaching towards something we can feel but cannot quite name. That reaching is not a failure. It is what it means to be a conscious creature in a universe that is stranger and more generous with its mysteries than anything we could have invented on our own. Here is something that should be impossible, and yet happens routinely in physics laboratories around the world. A particle, an electron or a photon, travels from one point to another. While it travels, it doesn't behave like a tiny object moving through space. It behaves like a wave, spread out, existing across multiple possible paths simultaneously, interfering with itself. And then a measuring instrument detects it, and suddenly it is a particle again, with a definite position, a definite momentum. The wave collapses. The possibility becomes a fact. What caused that collapse? the measurement, the observation, the act of looking. This is not a poetic interpretation. It is the mathematics of quantum mechanics, and it has been confirmed by experiment after experiment for nearly a century. The observer is not separate from what is being observed. The act of observation is not neutral. Something about the presence of a measuring system, and physicists still debate exactly what that means, changes what happens. This is what's known as the observer's paradox. And it reaches much further than physics. In social science, researchers have long noticed that when people know they are being studied, they change their behavior. Not always consciously, not always dramatically. But the observation itself introduces something that wasn't there before. The act of measuring a system becomes part of the system being measured. A sociologist studying a community, a psychologist conducting an interview, a camera placed in a public space, all of these change the thing they are trying to simply record. Even in ordinary life, this pattern appears. When someone is watching you, you become a slightly different version of yourself. When you watch yourself, when you become self-conscious, when you step back and observe your own thoughts, the thoughts change. Introspection is not a clean window into the mind. It is another act of the mind, and it shapes what it looks at. The observer and the observed are never fully separate. That thread runs from quantum physics all the way down to the most ordinary moments of human experience. And it quietly undermines the idea that there is a neutral, view-from-nowhere perspective available to anyone. Every observation comes from somewhere. Every measurement is made by something. There is no outside. Now step even further back from the human perspective. Not just to the level of the individual versus the observed, but outward, to the question of what reality looks like from entirely different kinds of minds. Because the reality you experience is not the only reality available to experience. It is the human reality. Tuned to human frequencies. Built for human survival on a particular kind of planet, in a particular range of environments, over a particular stretch of evolutionary time. A honeybee perceives ultraviolet light that is entirely invisible to you. Flowers that look plain and uniform to human eyes are, to a bee, covered in vivid patterns, landing guides painted in frequencies you have never seen and cannot imagine. The bee's reality contains colors you have no experience of. Not just colors you haven't seen. Colors your visual system is constitutionally incapable of perceiving. A dog lives in a world shaped primarily by smell in a way that has no real human equivalent. The information a dog receives from a single lamp post on a morning walk is, to that dog, something like reading a detailed social history of the neighborhood, who passed by, when, what they ate, how they felt, whether they were healthy or unwell. That information is simply absent from human reality. Not hidden. Not subtle. Just gone. As far as we are concerned. Bats navigate by sound in 3 dimensions with a precision that our finest sonar technology only approximates. Certain fish detect electric fields. Migratory birds appear to navigate by sensing the magnetic field of the Earth directly, perceiving something we have no sensory word for at all. Each of these creatures lives in what the biologist Jacob von Uexküll called an Umwelt, a self-world, a species-specific sensory envelope that constitutes the entirety of that creature's experienced reality. The tick waiting on a branch for years, sensing nothing but temperature and the smell of butyric acid from mammal skin. The starling in a murmuration responding to its 7 nearest neighbors in patterns of collective movement that look, from a distance, like something between mathematics and music. Each Umwelt is complete, internally consistent, a full world to the creature living in it. And each one is radically different from every other. Which raises a question that is simple to ask and surprisingly difficult to answer. Is there a reality that exists beneath all of these different perceptual worlds? An underlying truth that the bee's ultraviolet and the dog's smell and the human's language and reason are all, in their different ways, partial windows onto? Or are there simply the Umwelten, the experiential worlds, with no single master reality beneath them? We don't know. And the fact that we don't know matters. There's something else worth considering when it comes to perception and how it's built. Something that happens at the very beginning of a human life, before language, before memory, before almost anything we would recognize as experience. Newborn babies, in the first weeks of life, can see. Their eyes open, light enters, signals travel to the brain. But what they see is not what you see. Infant color vision is limited and slow to develop. The full range of color discrimination that most adults take completely for granted, the ability to distinguish thousands of subtle gradations of hue, is not present at birth. It emerges. It is built, gradually, through a combination of biological maturation and exposure to a world of colored things. And this is not just a minor technical footnote about infant development. It points to something important. The perceptual world we inhabit as adults is not simply given. It is constructed, over time, by a developing system shaped by experience. The richness of color that you see when you look at a garden or a sunset or a painting, that richness was assembled. It did not arrive prepackaged. Your visual world is richer than a newborn's, in ways the newborn cannot know, because they have no comparison to make. Which naturally leads to a question you're probably not supposed to take too seriously, but which is worth at least a moment of honest attention. How much richer might perception be, beyond what even an adult human can access? Not in some mystical sense. Simply in the same straightforward sense that adult color perception is richer than a newborn's. Are there entire dimensions of experience that human beings are constitutionally unable to perceive, the way a newborn cannot perceive the full color spectrum, not because the information isn't there, but because the receiving apparatus simply hasn't developed the capacity? We have no way to answer that from inside our own perceptual system. Which might be exactly the point. Here is a smaller mystery, one that most people have encountered personally and quietly filed away as unexplained. You are sitting in a room, or walking down a street, or riding in a vehicle. Your attention is elsewhere. And then, for no clear reason, you turn around. And someone is looking at you. You felt it before you had any sensory evidence of it. The feeling of being stared at. It's one of those common experiences that sits in a strange borderland. Surveys suggest the majority of people report having experienced it. And yet controlled experiments have produced stubbornly mixed results. Some studies find a small but statistically detectable effect. Others find nothing beyond chance. The question hasn't been cleanly resolved. What's interesting is not whether the phenomenon is real in a paranormal sense. That's a separate argument with a lot of history attached to it. What's interesting is what it reveals about the relationship between perception and belief. People experience it. They experience it consistently and confidently. And their experience doesn't wait for experimental confirmation. This is one of the places where individual reality and independent reality come apart most visibly. Something is happening. People are not lying about their experience. But whether what's happening is detection of a real external signal, or the result of pattern matching by a brain so finely tuned to social cues that it sometimes fires in the absence of evidence, we don't fully know. The brain that generates your experience of the world is exquisitely social. It evolved in conditions where reading other people, their attention, their intentions, their emotional states, was among the most important tasks it ever had to perform. A brain that occasionally generates false positives in social detection, that errs on the side of sensing a presence that isn't there, may be doing exactly what it was shaped to do. Better to turn around unnecessarily 100 times than to fail to notice the one time it matters. And then there is the friendship paradox, which sounds, when you first hear it, like it must be wrong. On average, your friends have more friends than you do. Not because you are unpopular. Not because there's something unusual about your social life. It is a mathematical property of networks. The people in your social circle who have the most connections appear in more people's friend lists. That means when you average across your friends, you are systematically oversampling the highly connected. The same paradox means that your followers on a social network likely have more followers than you. The people at your gym are probably, on average, going more regularly than you are. The other passengers on a flight have, on average, flown more times than you. This pattern, technically called the inspection paradox, appears throughout social and physical systems. And it subtly distorts our sense of where we stand relative to others. We compare ourselves not to a random sample of people, but to the people we are most likely to encounter, who are disproportionately the people who are most active, most connected, most visible. And so we consistently underestimate how ordinary our experience is, and overestimate how much more others are doing, having, experiencing. The world you use to measure yourself against is not a neutral sample. It is biased by the very structure of how connection works. Now, all of these observations, about quantum observers and animal perception and infant vision and social illusions, eventually lead somewhere larger. They accumulate into questions that human beings have been wrestling with formally for at least 2,500 years, and informally for as long as there have been minds to wonder. These questions live in the branch of philosophy called metaphysics. Metaphysics is the attempt to understand the fundamental nature of reality. Not what the world contains, but what the world is. Not which physical laws govern matter, but what matter is at the deepest level. Not what exists, but what existence means. metaphysics asks the questions that sit beneath all other questions. And while it sometimes gets dismissed as abstract or impractical, almost every deep assumption embedded in science, law, ethics, and ordinary life turns out, on examination, to be a metaphysical assumption dressed in practical clothes. One of the oldest and most enduring debates in metaphysics is the debate between realism and anti-realism. Realism, in its most basic form, is the view that the world exists independently of any mind observing it. Mountains, rivers, atoms, stars, these things were real before any conscious creature came along to perceive them, and they would be real if every conscious creature disappeared tomorrow. Reality is out there. It doesn't need us. Anti-realism questions this. In various forms, anti-realism suggests that reality as we know it is shaped by, dependent on, or in some cases constituted by minds. That the independent, mind-free reality the realist describes is either unknowable or incoherent as a concept, or simply not what we mean when we use the word real. The world we have access to is always a world for us, shaped by our conceptual frameworks, our languages, our perceptual systems. This isn't just a philosophical word game. It has consequences. If realism is right, then science is in the business of discovering truths that were always there, waiting to be found. If anti-realism is right, then science is in the business of constructing useful models within the limits of human understanding, which is a different thing entirely. Both views produce the same equations and the same experiments. But they mean very different things about what those equations and experiments are actually doing. Running alongside this debate, and sometimes crossing it in interesting ways, is the older opposition between materialism and idealism. Materialism is the view that everything that exists is, at bottom, physical. Mind, consciousness, experience, love, mathematics, music, all of it ultimately reduces to matter and energy and the interactions between physical things. Consciousness is what certain arrangements of matter do. Experience is a product of neural activity. There is nothing in the universe that is not, in some sense, made of stuff. Idealism is the view that the fundamental nature of reality is mental. Not that matter doesn't exist, but that matter exists within or as a form of consciousness, rather than the other way around. The most famous version of this was proposed by George Berkeley in the early 18th century. Objects exist only as perceptions. To be is to be perceived. The tree in the forest, when no one is there to see it, exists as a perception in the mind of God, or, in secular versions of the argument, as a kind of standing potential for experience, rather than as a solid independent thing. Modern physics has given idealism an unexpected second wind. The measurement problem in quantum mechanics, the fact that particles seem to exist in superpositions of possible states until observed, has led some physicists and philosophers to take seriously the idea that consciousness plays a constitutive role in physical reality, not just a descriptive one. And then there is a view that tries to dissolve the opposition between these two altogether. Panpsychism is the idea that consciousness, or something like it, is not a special property that appears only in complex brains. It is a fundamental feature of reality, present in some form at every level. Not that rocks and electrons have thoughts or feelings in any human sense, but that the capacity for experience, for some form of interiority, is woven into the fabric of existence at the most basic level, and that what we call human consciousness is simply the most elaborate expression of something that was always, at some scale, present. This sounds strange to modern ears, shaped as we are by the assumption that mind is something that emerges from matter under special conditions. But panpsychism has a long intellectual history, and it has attracted renewed serious attention precisely because the alternative, explaining how subjective experience arises from purely physical processes, has proven so stubbornly, persistently difficult. The so-called hard problem of consciousness is this: you can explain, in principle, how the brain processes light and produces a response to it. You can map the neural correlates of every perceptual event. But none of that explanation touches the question of why there is something it feels like to see red. Why the processing is accompanied by experience. Why the lights are on, from the inside. No one has solved this. Not with current tools, and possibly not with any tools we can currently imagine. And panpsychism suggests that maybe the reason it's so hard is that we've been looking in the wrong direction, trying to explain how mind emerges from mindless matter, when the question should be why we ever assumed matter was mindless to begin with. These debates, realism and anti-realism, materialism and idealism, panpsychism and its critics, are not historical curiosities. They are alive. Philosophers and physicists and cognitive scientists are still arguing about them, still finding new angles, still discovering that each apparent resolution opens new questions. And perhaps that is the most truthful thing that can be said about the great philosophical debate over the nature of reality. It is not a debate that is converging on a settled answer. It is a debate that is deepening. Each generation of thinkers inherits the questions in a richer form than the one before. The territory being mapped keeps expanding as new instruments reveal new features of the landscape. There is, in that fact, something both humbling and strangely comforting. Humbling, because it means that the confident certainties of any particular era, including ours, are likely to look, from the future, like the beginning of understanding rather than the end of it. And comforting, because it means the questions are still alive, still open, still genuinely anyone's to think about. The night is quiet. The mind is soft. And somewhere beneath all the words, beneath realism and idealism and panpsychism and paradox, the universe continues doing what it has always done. Existing, in whatever way it exists. Whether or not anyone is watching. There is a deeply ingrained habit in modern thinking, so common that most of us don't notice it as a habit at all. When we want to really understand something, we take it apart. We look at what it's made of. We reduce it to its components, and then we reduce those components further, and we keep going until we reach something that feels fundamental, something that cannot be broken down any further. And then we say, now we understand it. This approach is called reductionism. And it has been, without any exaggeration, one of the most productive intellectual strategies in human history. Because of reductionism, we know that water is made of hydrogen and oxygen. We know that living organisms are built from cells, and that cells are built from molecules, and that molecules are built from atoms, and that atoms are built from smaller particles still. We know that diseases have physical causes, that mental states have neural correlates, that the apparent solidity of a table is actually a vast amount of empty space populated by forces of electromagnetic repulsion. Reductionism opened the physical world in ways that nothing else could, and the benefits have been staggering in medicine, in technology, in our basic understanding of nature. And yet, there is a growing recognition, cutting across multiple disciplines simultaneously, that reductionism alone is not enough. That it is a powerful tool, but not the only tool. And that in some domains, the insistence on reducing everything to its smallest components actively obscures what is most important. Consider music. You can, in principle, describe any piece of music entirely in physical terms. Air pressure waves at specific frequencies, arriving at specific intervals, causing specific mechanical responses in the inner ear, triggering specific patterns of neural firing. All of that is true. All of it is verifiable. None of it captures what music is. The grief in a cello phrase. The way a particular chord progression creates a feeling of longing that has no object. The moment when a melody resolves and something in you releases. These are not mystical additions to the physical description. They are real features of what music is. And the reductionist account, however complete on its own terms, simply does not reach them. Or consider consciousness itself. Neuroscience has made extraordinary progress in mapping the brain. We know which regions activate during which experiences. We can watch, in real time, the patterns of electrical activity that accompany thought and emotion and perception. But the fact that there is something it is like to have those experiences, that hard inner glow of awareness, that quality of being on the inside of a life, that fact is not explained by the map. The map is of the territory. It is not the territory. Or consider ecosystems. An ecosystem is not simply a collection of organisms. It is a web of relationships, feedbacks, dependencies, and balances so intricate that removing a single species can cascade through the entire system in ways that no analysis of the individual parts would predict. The whole has properties that genuinely do not exist in any of the parts. The parts, studied in isolation, give you no access to those properties at all. This is what philosophers call emergence. The appearance of properties and behaviors at higher levels of organization that cannot be predicted from or reduced to the behavior of lower-level components. Wetness is not a property of individual water molecules. Flocking behavior is not contained in any single bird. The meaning of a sentence is not located in any individual word. These things arise from interaction, from relationship, from organization, and they are no less real for being irreducible. The critique of reductionism is not a rejection of science. It is an expansion of what science needs to look at. It is the recognition that the universe organizes itself into levels, and that each level has its own properties, its own laws, its own way of being real. And that the microscopic level, however foundational it may be in one sense, is not automatically more real, more true, more important than the levels above it. This is a point worth dwelling on, because it runs counter to a very deep intuition that modern thinking has installed in most of us. The intuition that small equals fundamental, and fundamental equals more real. That if you want the truth about something, you should always look deeper, smaller, further down. But why should the arrangement of quarks inside a proton be more real than the heartbeat of the animal they are part of? Why should the electrochemical signals in a brain be more real than the decision being made, or the love being felt, or the poem being written? The signals are the substrate. They make the higher level events possible. But they are not more real. They are differently real. They are real at a different level of organization. Reductionism became the dominant intellectual strategy of the modern era for reasons that are historically understandable. It worked enormously and repeatedly. Beginning with the scientific revolution and accelerating through the industrial age, the strategy of breaking things down into parts and studying the parts produced results that were, by any measure, spectacular. Diseases were cured. Machines were built. The atom was split. The genome was sequenced. The universe was traced back to its first few moments. And because it worked so consistently, it began to feel like more than a strategy. It began to feel like a metaphysical truth. As though the universe itself was telling us that its deepest nature was to be found at the smallest scales. But this is a conflation. What was shown is that breaking things down into parts is a productive way to learn certain kinds of things. What was not shown, and cannot be shown by that method alone, is that the parts are what the whole ultimately is. The method and the metaphysics are not the same. And the places where reductionism quietly fails, in consciousness, in meaning, in ecology, in culture, in the emergent complexity of living systems, these are not embarrassing gaps to be eventually filled. They are signals that the universe has a structure that requires more than one kind of understanding. Many viewpoints, many levels of description, many modes of inquiry, not as a compromise, but as a genuine reflection of how reality is layered. This is not relativism. It is not the claim that all explanations are equally valid. It is the more careful claim that reality presents itself differently at different scales, and that a full account of it requires tools appropriate to each level. That recognition is slowly, quietly reshaping fields as different as physics and psychiatry, ecology and economics. The conversation is far from settled, but the direction is clear. The single lens is giving way, gradually, to many lenses held together. And the picture that results is richer, stranger, and more adequate to the actual complexity of what exists. Now, let's leave the question of levels and scales for a moment and move into territory that is, in its own way, even more unsettling to ordinary intuition. Because ordinary intuition, it turns out, has been wrong about some very basic things. Not subtly wrong. Not wrong around the edges. Wrong at the center, about the nature of space, and the nature of time, and the relationship between them. The intuitive picture of time is something like this. Time flows. It moves forward, at a steady pace, the same for everyone everywhere. While you sit reading or listening, the same moment is unfolding on the other side of the world, and on the moon, and in distant galaxies. The universe has a common now. Clocks, wherever they are placed, tick at the same rate. This picture is wrong. It is not approximately right. It is not right in ordinary conditions and wrong in exotic ones. It is, at a fundamental level, a misrepresentation of what time actually does. What time actually does is this: it passes at different rates depending on how fast you are moving, and how strong a gravitational field you are in. This is time dilation. It is one of the most thoroughly tested predictions in all of physics, confirmed by experiment after experiment across more than a century. And it means that two clocks, placed in different conditions, will genuinely, physically, measurably accumulate different amounts of time. Not because one is broken, not because of any error in measurement, but because time itself passes differently for them. The faster you move through space, the slower you move through time. This is not a paradox or a trick of language. If you were to travel away from Earth at a significant fraction of the speed of light and return, less time would have passed for you than for the people you left behind. You would be younger than you would have been had you stayed. Not subjectively younger. Not feeling younger. Actually, physically, biologically younger. The atoms in your body would have experienced fewer moments. At everyday speeds, this effect is vanishingly small. You would need extraordinarily precise instruments to detect it. But those instruments exist, and they do detect it. In the 1970s, physicists flew extremely accurate atomic clocks on airplanes and compared them, after the flights, to identical clocks that had remained on the ground. The clocks on the planes showed slightly less elapsed time than the clocks on the ground. Not by much. By nanoseconds. But the difference was there, consistent, and exactly matched the predictions of relativity. Today, this is not an experiment. It is an engineering requirement. The satellites of the GPS system orbit the Earth at high speed and at significant altitude, which means they experience both the time-slowing effect of velocity and the time-speeding effect of reduced gravity. These two effects partially cancel, but not completely. The net result is that GPS satellite clocks run at a different rate than clocks on Earth's surface. If the system's software didn't correct for this continuously, if it simply assumed that all clocks everywhere tick at the same rate, GPS navigation would accumulate errors of kilometers per day. The relativity correction is not theoretical. It is built into the system. You use it every time you ask your phone for directions. What Einstein revealed, in his theory of special relativity published in 1905, and then in the general theory that followed a decade later, is that space and time are not separate, independent things. They are two aspects of a single four-dimensional structure he called space-time. In everyday life, we move through three dimensions of space and experience time as something separate, a flow, a current, an arrow. But this separation is an artifact of how slowly we move compared to light. At higher velocities, the interweaving of space and time becomes impossible to ignore. Moving faster through space means moving more slowly through time. The two are not independent quantities. They are like the length and width of a single surface. You can describe them separately, but they are aspects of one thing. Gravity, in this framework, is not a force in the traditional sense. It is not an invisible hand reaching across space to pull masses together. It is a curvature in spacetime itself, caused by the presence of mass and energy. A massive object like the Sun doesn't pull the Earth toward it. It curves the spacetime around it, and the Earth moves in a straight line through that curved geometry, a straight line that, from our perspective, looks like an orbit. This is one of those ideas that the mind resists, not because it's poorly explained, but because it runs so deep beneath ordinary experience that no ordinary analogy quite captures it. The closest intuitive picture is something like a heavy ball placed on a stretched rubber sheet. It creates a depression, and smaller objects rolling nearby follow curved paths around it. But this analogy is imperfect in important ways. The real thing is happening in 4 dimensions, not 2, and what is curving is not a physical surface but the geometry of existence itself. Time, in this picture, passes more slowly in stronger gravitational fields. Deep in a gravitational well, closer to a massive object, time runs slower than it does further away. This is gravitational time dilation, and it too has been measured. Clocks at sea level, sitting deeper in Earth's gravitational field, tick fractionally slower than clocks on mountaintops. The difference is tiny, but it is real. There is another effect from special relativity that is, if anything, even harder for ordinary intuition to absorb. Length contraction. An object moving at high velocity does not just experience time differently. It is also shorter, in the direction of its motion, than it would be if it were stationary. Not appearing shorter due to perspective. Actually shorter. The physical length of the object, measured in the frame of someone watching it pass, is genuinely contracted. At everyday speeds, this contraction is immeasurably small. But it scales with velocity, and at speeds approaching the speed of light it becomes dramatic. A meter stick moving past you at 99% the speed of light would be about 14 centimeters long, measured in your frame of reference. From the perspective of someone moving with the meter stick, it would be a perfectly normal meter stick. Both measurements are correct. Neither frame of reference is the true one. There is no view from nowhere against which one reading is right and the other is wrong. And this brings us to what may be the deepest consequence of all of this. Properties are relational. Length is not a fixed property of an object. It depends on the relative motion between the object and the observer. Duration, how long an event lasts, is not a fixed property of the event. It depends on the relative velocity and gravitational position of whoever is measuring it. Simultaneity, whether 2 events happen at the same time, is not an objective fact. 2 events that are simultaneous in one frame of reference are not simultaneous in another, and there is no privileged frame that settles the question. These are not philosophical opinions. They are empirical results. The universe, examined carefully, does not have the fixed, absolute, observer-independent geometry that ordinary experience suggests. What exists are relationships. What exists are intervals, the space-time separation between events, which are invariant. Not the space component alone, not the time component alone, but the combined space-time interval, which all observers agree on. It is a deeper kind of constancy, hiding beneath the relativity of the surface properties. The universe is not relative all the way down. But the things it turns out to be absolute about are not the things we thought. Not the length of a rod. Not the duration of an event. Not the order of events separated in space. The invariant quantities are more abstract, more structural, the fabric beneath the appearances rather than the appearances themselves. What this means for the nature of reality is still being worked out. It means that the properties we observe, the measurements we make, are not simply readings of mind-independent facts about isolated objects. They are facts about relationships between objects, or between objects and observers, embedded in a four-dimensional structure that is itself dynamic, warped by mass, stretched by expansion, rippled by the motion of massive bodies colliding across cosmic distances. The universe is not a collection of things with fixed properties sitting in a fixed space, ticking forward through a fixed time. It is something far more fluid, far more interconnected, far more alive, in a sense, than the static mechanical picture suggests. And when you lie still in the quiet of a late night and the mind grows soft and the ordinary certainties of the day begin to loosen their grip, perhaps that loosening is not confusion. Perhaps it is something closer to accuracy. The fixed, solid, clearly bounded world of waking habit is a simplification. A useful one. A necessary one for getting through the day. But beneath it, the universe is doing something much stranger. Time is bending. Distances are shifting. The now that you occupy is yours alone, not shared, not universal, not the same as the now happening anywhere else. And the properties of everything around you are not sitting there waiting to be measured. They are emerging, moment by moment, from the geometry of relationship. There is nothing in that picture that asks you to be afraid. Only to be, perhaps, a little more humble about the edges of what we know. And a little more open to the possibility that reality, full, actual, physical reality, is already far more extraordinary than anything we needed to imagine or invent. It was always this strange. We just had to look carefully enough to see it. One of the quieter revelations of modern physics is that some of the most basic things we assume to be fixed and universal turn out to depend entirely on who is asking. Take something as fundamental as the number of particles in a region of space. In ordinary experience, counting seems like the most objective thing imaginable. Either there are 3 apples on the table or there aren't. The number doesn't change depending on whether you are standing still or moving past. Counting is counting. But in quantum field theory, the branch of physics that most precisely describes the behavior of matter and energy at the smallest scales, this assumption breaks down in a way that is deeply strange and has no intuitive parallel. Whether a region of space contains particles, whether it reads as empty or occupied, depends on the state of motion of the observer. An observer moving with constant acceleration through what another observer measures as a perfect vacuum will detect a warm bath of particles. The vacuum, from an accelerating frame of reference, is not empty. It glows. This is known as the Unruh effect, and while it has not yet been directly measured, the acceleration required to produce a detectable temperature is enormous by any practical standard. it follows from the same theoretical framework that has been confirmed in hundreds of other contexts. What this means is that particle number is not an absolute fact about the world. It is a relational fact. It depends on the observer's trajectory through space-time. Two observers, both using valid physics, both doing everything correctly, will disagree about whether a given region of space contains particles. And neither of them is wrong. They are measuring different things because they are different things, physically speaking, different trajectories, different relationships to the quantum fields that fill all of space. This is not a technicality. It is a fundamental feature of how the universe works at its deepest accessible level. The most basic inventory of what exists, how many particles are present, is not observer independent. It is woven into the relationship between the measuring system and the thing being measured, all the way down. Reality, again, turns out to be relational rather than absolute. The pattern keeps appearing, at every scale, in every domain. Now step back from the very small to the very large. From quantum fields to the night sky. When you look up at the stars on a clear night, you are not seeing the universe as it is. You are seeing the universe as it was. Every point of light in the sky is a message from the past, and the further away the source, the further back in time the message was sent. The light from the moon takes about 1¼ seconds to reach you. When you look at the moon, you are seeing it as it was a little over a second ago. The light from the sun takes roughly 8 minutes to arrive. If the sun were to somehow vanish entirely right now, you would not know for 8 minutes. You would continue to see it, warm and apparently unchanged, while the reality had already shifted. The nearest star beyond our sun, Proxima Centauri, is about 4 light-years away. The light reaching your eye from it tonight left its surface 4 years ago. What Proxima Centauri looks like right now is information that has not arrived yet and will not arrive for 4 more years. And the further you look, the more dramatic this becomes. Many of the stars visible to the naked eye are hundreds of light-years away. Some of the objects visible through telescopes are billions of light-years distant, meaning the light arriving at the instrument tonight left its source before the Earth existed. We are looking at a universe that no longer is. We are archaeologists of light, reading a record of what was, with no direct access to what is. The entire observable universe is, in a precise sense, a history. Not a picture of now. A picture assembled from signals that left their sources at different moments across billions of years of cosmic time, all arriving at this particular point in space simultaneously, producing the impression of a single present sky. There is no way to see the universe as it currently is. The speed of light makes that impossible in principle, not just in practice. The present state of the cosmos is, for any observer within it, permanently inaccessible. Every observation is an observation of the past. And this applies not just to distant stars but to everything. The image of a friend's face takes time to travel from their skin to your eye. The sound of a voice takes time to cross a room. The gap is so small as to be irrelevant in daily life. But the principle is the same. You have never perceived anything as it is in this precise instant. You have always and only ever perceived things as they very recently were. the present moment, as a shared universal fact, does not exist. What exists is a web of overlapping, slightly offset pasts, each one the present as experienced from a particular location. The universe does not have a single now. It has countless local nows, all slightly out of step with each other. Now come back to Earth. All the way down to its surface, its slow turning, and a change so gradual it is invisible to any individual life. The Earth's rotation is slowing down. Not dramatically. Not in any way you would notice across a human lifetime. But measurably, steadily, over geological time, the length of a day on Earth is increasing. The mechanism is primarily tidal friction. The Moon's gravity raises tidal bulges in Earth's oceans, and as the Earth rotates beneath those bulges, friction is generated. That friction acts as a brake. Angular momentum is transferred from Earth's rotation to the Moon's orbit, causing the Moon to gradually spiral outward and the Earth to spin more slowly. The effect is tiny by human standards, roughly 1.4 milliseconds per century. But over the vast timescales of Earth's history, it adds up enormously. When the Earth was young, approximately 4.5 billion years ago, a day was likely only around 6 hours long. The planet was spinning much faster, the Moon was much closer, and the forces involved were far more violent than anything the modern Earth experiences. Ancient coral fossils carry a record of this. Because corals lay down daily and annual growth rings, careful examination of very old coral specimens reveals how many days there were in a year during the period those corals were alive. And in ancient corals, the count is higher, more days per year, meaning shorter days. The year hasn't changed in length in any meaningful way, because Earth's orbit around the Sun is not affected by the same mechanism. But the day has changed, slowly and continuously, throughout Earth's entire history. A day, in other words, is not a constant. The unit of time we use to organize our entire lives, our calendars, our rhythms of sleep and waking and work and rest, it has changed, is changing still, and will continue to change for as long as the Earth and Moon remain in their current relationship. There is something quietly vertiginous about this. The most fundamental rhythm of terrestrial life, the cycle of light and darkness that has governed every living thing on this planet for billions of years, is not fixed. It is a moving target, drifting with geological slowness but drifting nonetheless. And there is one more small, quietly wonderful thing about time and the human body before we leave this earthly scale entirely. Astronauts who spend extended periods on the International Space Station return to Earth slightly taller than when they left. Not permanently. Within a few months of returning to Earth's gravity, their height returns to normal. But during their time in space, freed from the constant compression of gravity, the cartilage between the vertebrae and the spine expands. The spine decompresses. Astronauts can gain as much as 5 to 8 centimeters in height during a long-duration spaceflight. The human body, it turns out, is partly defined by the force pressing down on it. Remove that force, and the body assumes a different shape, its space shape, its zero-gravity self. The height you have always thought of as simply yours, fixed and biological, is partly a product of your relationship to Earth's gravitational field. In a different gravitational environment, you would be measurably different. Everything, it seems, is more relational than it first appears. Now move further out. Further than astronauts go. Further than satellites orbit. Further than the farthest human artifact drifting through interstellar space. Out to the scale where the universe reveals its deepest and most humbling strangeness. Because what physics has found, when it examines the universe at cosmological scales, is that the ordinary matter we know, atoms, molecules, stars, planets, gas clouds, everything that has ever been seen or touched or measured directly, constitutes only about 5% of everything that exists. 5%. The rest of the universe is made of things we cannot see, cannot touch, and do not yet understand. About 27% of the universe, by current best estimates, is what cosmologists call dark matter. It does not emit light. It does not absorb light. It does not interact with ordinary matter through electromagnetism in any way that we have detected. It is, in the most literal sense, invisible. We know it exists because of its gravitational effects. Galaxies rotate in ways that cannot be explained by the mass of their visible stars. Light from distant sources bends as it passes through apparently empty regions of space, indicating the presence of enormous gravitational mass that no telescope can locate. The large-scale structure of the universe, the way galaxies cluster in the vast cosmic web of filaments and voids, matches precisely what models predict if dark matter exists in the quantities and distribution we infer. But what dark matter is, at a fundamental level, remains unknown. It is not any particle we have discovered or currently have the ability to detect directly. It may be a new kind of particle entirely, something outside the standard model of physics. It may be something stranger still. For now, it is defined almost entirely by what it is not. And then there is the remaining 68%. The largest component of everything. Dark energy. Dark energy is not just unknown, it is, in some ways, almost conceptually opposite to what physics previously expected. Where gravity draws things together, dark energy appears to be driving the expansion of space itself, and driving it at an accelerating rate. The universe is not just expanding. It is expanding faster and faster, pushed apart by something distributed uniformly throughout all of space, something that does not dilute as space expands the way matter and energy do, something that may be a property of space itself, the energy of the vacuum, a constant repulsive pressure built into the geometry of existence. If dark energy continues to dominate, the long-term fate of the universe is one of increasing isolation. Distant galaxies are already receding from us faster than the speed of light, not because they are moving through space at that speed, but because the space between them and us is expanding so rapidly. Eventually, in the far future, the observable universe will shrink as more and more galaxies recede beyond the cosmological horizon. The night sky will go dark, one region at a time, as the light from distant sources can no longer reach us. We live, it appears, in a universe whose dominant constituents are invisible to every instrument we have ever built, and whose ultimate fate is driven by a force we have no physical theory adequate to explain. Meanwhile, closer to home, we are surrounded by a protection so vast and so invisible that it rarely crosses anyone's mind. Earth is enveloped in a magnetic field generated by the movement of molten iron in its outer core. This field extends far out into space, creating a region called the magnetosphere that deflects the constant stream of charged particles flowing outward from the sun, the solar wind, or around the planet rather than letting them strike the surface directly. Without this shield, those particles would strip away the atmosphere over geological time. Mars, which lost its magnetic field billions of years ago, also lost most of its atmosphere. Where Mars once likely had liquid water on its surface, it is now a cold, thin-aired, radiation-scoured world. Earth's magnetic field is one of the reasons complex life was able to develop here, and it is something so thoroughly out of sight and out of mind that the vast majority of the people it protects will go their entire lives never thinking about it once. The field is not static. It fluctuates in strength and has, over Earth's history, reversed its polarity hundreds of times, the North Magnetic Pole and the South Magnetic Pole swapping places, over timescales of thousands of years. The field weakens during these transitions, and while life on Earth has clearly survived previous reversals, the long-term effects of the current period of weakening, the field has lost roughly 9% of its strength over the last century and a half, remain a subject of genuine scientific attention. We are, right now, moving through such a period. The invisible armor is changing. Not failing, but shifting. And most of us will never know. Now look up again. Back to the night sky. And notice something that, once pointed out, is very hard to stop thinking about. The sky at night is dark. This seems obvious. Of course it is dark. It's night. The sun is set. But wait. If the universe is infinite, and if stars are distributed throughout it in all directions, then for every line of sight you cast outward into space, that line should eventually intersect a star. The sky should be uniformly, blindingly bright in every direction, at every hour. The darkness of the night sky, in an infinite static universe, should be impossible. This puzzle is known as Olbers' paradox, after the 19th century astronomer Heinrich Olbers, who brought it to wide attention, though others had noticed it before him. And it is a genuine paradox, not a wordplay contradiction, but a real conflict between a seemingly reasonable assumption and an obvious observable fact. The resolution lies in several factors that Olbers did not have access to. The universe is not infinitely old. It has a finite age, approximately 13.8 billion years, which means light from stars beyond a certain distance has not had time to reach us. The observable universe is bounded not by space but by time. And the universe is expanding, which means light from distant sources is redshifted, its energy stretched out and diminished as space expands beneath it. Many sources that emit light at visible wavelengths have their radiation shifted into the infrared or microwave, invisible to the eye. The darkness of the night sky is not a simple absence. It is evidence of cosmological history. It is a consequence of the age and expansion of the universe, written across the entire visible sky every clear night. The darkness is data. And then there is perhaps the most haunting data of all. The question that physicist Enrico Fermi reportedly posed, simply and without ceremony, over lunch in 1950. Where is everybody? The universe is approximately 13.8 billion years old. It contains somewhere in the range of 2 trillion galaxies, each containing hundreds of billions of stars, many of those stars orbited by planets, many of those planets likely capable of supporting liquid water. By almost any reasonable estimate, the conditions for life should have arisen many times, in many places, long before the Earth existed. Civilizations with billions of years head start on us should, if they developed anything like our own technological trajectory, have had time to colonize the galaxy many times over. And yet, we have found no signal, no artifact, no unambiguous trace of any intelligence beyond our own. The silence is, on the face of it, extraordinary. This is the Fermi paradox. Not a paradox in the technical logical sense, but a deep and unresolved tension between what the numbers suggest should be out there and what our search has actually found. The proposed explanations range across a remarkable spectrum. Perhaps life is far rarer than we think, and the conditions that produced Earth were so unlikely that we are, functionally, alone in the observable universe. Perhaps intelligence reliably destroys itself before it can expand, through war, environmental collapse, or technologies it cannot control, and the silence is a graveyard. Perhaps civilizations tend to go inward rather than outward, into virtual or post-physical existence, rather than colonizing space. Perhaps we are being observed but not contacted, deliberately left to develop without interference. Perhaps the physics of interstellar travel is a hard enough barrier that no civilization has crossed it. Perhaps we simply haven't been looking long enough, or in the right ways. None of these explanations is clearly right. None is clearly wrong. The question remains genuinely open, and it remains one of the most profound unanswered questions in all of science. Because the answer, whatever it is, says something fundamental about the nature of life and intelligence in the universe, and about our own situation within it. And somewhere in that same vast universe, distributed through the cosmos in quantities we can barely conceptualize, there are planets made of diamond. Carbon, under sufficient pressure and heat, can crystallize into diamond. Certain types of stars process carbon and oxygen in proportions that, under the right conditions, lead to worlds where the interior is not silicate rock and iron, as the Earth's is, but carbon, potentially including layers of diamond created by the pressures of planetary formation. Some white dwarf stars, at the end of their lives, are believed to undergo a process in which their carbon cores crystallize. The most famous candidate is BPM 37093, a white dwarf about 50 light-years away, whose crystallized carbon core has been estimated to be the size of Earth and has been, with a certain poetic enthusiasm, nicknamed Lucy, after the Beatles' song. The universe makes diamond on a planetary scale, in conditions and at sizes utterly beyond anything the human world can frame. It does this not as an exception or a rarity, but as a natural consequence of its physics, in countless places across countless galaxies. The ordinary facts of cosmology, taken seriously, produce a kind of sustained astonishment that nothing else quite matches. Not because the universe is trying to impress anyone. It isn't. It is simply doing what physics does, at scales and in modes that our perceptual systems were never built to grasp, with a casual extravagance that makes human grandeur look like a very small and very quiet thing. And perhaps that smallness is not diminishing. Perhaps it is clarifying. To be a conscious creature capable of wondering about dark matter and silent skies and diamond planets, that is not nothing. That is, as far as we know, something the universe does rarely if at all. The wondering itself may be among the most remarkable things happening anywhere in the observable cosmos. It is late. The stars are out, each one a message from a past you will never directly reach. And beneath you, the earth turns, slightly more slowly than it did yesterday, under a shield you cannot see, through a universe mostly made of things no one yet understands. Rest in that. It is a strange and generous darkness. Venus is, in many ways, the most hostile world in the solar system. Its surface temperature is hot enough to melt lead. Its atmosphere is a crushing blanket of carbon dioxide 90 times denser than Earth's, laced with clouds of sulfuric acid. The pressure at the Venusian surface is equivalent to being nearly a kilometer underwater. And it rains, not water, but sulfuric acid, which evaporates before it ever reaches the ground in the extreme heat below. But there is one detail about Venus that manages to be strange even against that backdrop. On the highest mountain ranges of Venus, it snows metal. At lower altitudes, the surface is too hot for any metal compounds to remain solid. But at the peaks of the highest Venusian highlands, temperatures drop just enough that certain metallic compounds, most likely bismuth sulfide and lead sulfide, condense out of the atmosphere and settle on the terrain as a bright metallic frost. The mountaintops of Venus glitter. Radar images from orbiting spacecraft show the high elevations as unusually reflective, coated in this strange metallic deposit that forms and reforms as the Venusian atmosphere moves across the summits. A world with acid rain, crushing pressure, and temperatures that never drop below 400 degrees Celsius, and at its peaks, metal snow. The solar system does not run short of the extraordinary. And then there is a different kind of extraordinary, quieter and closer to home. Not distant and dramatic, but immediate and largely unexplored. We know the surface of Mars better than we know the floor of our own oceans. This is not an exaggeration. Mars has been mapped in extraordinary detail. Orbiters have photographed virtually its entire surface at high resolution. Rovers have crawled across its terrain for years, drilling into rocks, analyzing soil chemistry, measuring atmospheric pressure, documenting the landscape in 360-degree panoramas that anyone on Earth can view. We have detailed topographic maps of Mars. We know the heights of its mountains and the depths of its canyons to a high degree of accuracy. The deep ocean floor of Earth, by contrast, remains largely unmapped at comparable resolution. Roughly 80% of the seafloor has not been directly surveyed in detail. The technology required to map the ocean floor is in some ways more demanding than the technology required to photograph a planetary surface from orbit. Water absorbs and scatters signals in ways that make high-resolution seafloor mapping slow, expensive, and logistically complex. The result is that we have more precise maps of the Moon, of Mars, and of several other planetary bodies than we have of the bottom of our own ocean. What we do know about the deep ocean suggests it is among the most alien environments on Earth. Below about 200 meters, sunlight fades and then disappears entirely. Below 1,000 meters, the ocean is in permanent, total darkness, a darkness more complete than anything experienced on the surface world, unbroken by seasons or weather or any cycle of light. The pressure increases steadily with depth, reaching crushing extremes in the deepest trenches. The temperature in the deep ocean sits just above freezing almost everywhere. And yet life is present. Not sparse, barely surviving life, but diverse, abundant, and in many places densely populated life. The deep ocean contains ecosystems built around hydrothermal vents, fissures in the seafloor where geothermally heated water emerges, rich in minerals, supporting communities of organisms that derive their energy not from sunlight but from chemical reactions. These chemosynthetic ecosystems were unknown to science until 1977. They represent an entirely different model of how life can work, not dependent on the sun, not part of the photosynthetic food chain that connects almost everything else alive on Earth, but running on the energy of the planet itself. The deep ocean is not simply a dark, empty version of the shallower sea. It is a different world. One we have barely entered. There is a geographical fact about the ocean surface that most people have never thought about, but which, once encountered, is quietly difficult to let go of. The surface of the ocean is not flat. It has hills and valleys, rises and depressions, in patterns that directly mirror the topography of the seafloor thousands of meters below. Where there is an underwater mountain range, the ocean surface above it is very slightly elevated, raised by fractions of a meter by the gravitational pull of the extra mass below. Where there is a deep trench, the surface dips very slightly downward. The difference in surface height is small, a matter of centimeters over horizontal distances of hundreds of kilometers, too subtle to see, far too subtle to feel on a boat. But it is measurable by satellite altimetry, and it has been used to map the broad structure of the seafloor from orbit, producing the most complete global picture of submarine topography available. The ocean surface is a map of what lies beneath it. The shape of the water above tells the story of the rock below. The boundary between sea and air is not divorced from the deep world under it. It carries its imprint, faintly but measurably, all the way to the surface. Connections running through apparently separate layers. Signatures of the deep showing up at the surface. It is a pattern that keeps appearing, at every scale, in domains you wouldn't necessarily think to connect. Now go smaller. Much smaller. Down through the water column and the rock, past the molecular level, past the atomic, into the structure of matter itself. Because matter, at the level where physics can actually examine it, is almost nothing like the solid, substantial stuff of ordinary experience. An atom consists of a nucleus surrounded by electrons. The nucleus is tiny beyond any ordinary intuition. If an atom were the size of a cathedral, the nucleus would be roughly the size of a fly at the center of it. The electrons occupy the vast surrounding space, but they are not small solid balls orbiting like planets. They are quantum objects with no definite position, existing as probability distributions spread through the available volume. What this means is that an atom is, by volume, overwhelmingly empty space. Not mostly empty space in the sense of having a lot of room between things. Almost entirely empty space, in proportions that the mind cannot really visualize. The material substance of the nucleus and the electrons accounts for a vanishingly small fraction of the total volume of the atom. And since everything you see, everything you touch, every object and surface and structure in the world is made of atoms, everything is, by volume, overwhelmingly empty space. The chair, the floor, the body, all of it almost entirely nothing, held in the shape of something by the forces between particles that are themselves almost dimensionless. This raises an immediate question that most people ask when they first encounter this fact. If matter is mostly empty space, why can't I put my hand through this table? The answer is that solidity, as we experience it, is not the result of matter being densely packed. It is the result of electromagnetic forces. When your hand approaches the table, the electrons in the outermost atoms of your hand and the electrons in the outermost atoms of the table repel each other with enormous force, like charges repelling like charges. This electromagnetic repulsion is what you feel as resistance, as hardness, as the sensation of solidity. You never actually touch anything. Not in the sense of your matter contacting other matter directly. What you experience as touch is always the electromagnetic interaction between the electron clouds of your atoms and the electron clouds of the atoms in whatever you are apparently in contact with. There is always a gap, always a force field mediating the interaction, always an invisible buffer between your matter and the matter of the world. The feeling of holding something, of standing on solid ground, of the reassuring pressure of a surface beneath you, all of it is the experience of electromagnetic repulsion, happening across distances too small to conceive of but too large, at the particle level, to constitute actual contact. Touch, that most intimate and immediate of senses, is always action at a distance. Now go deeper still. Past the atomic scale, past the electron clouds and the nucleus, into the behavior of the particles themselves. One of the most thoroughly confirmed and most conceptually disorienting discoveries in the history of physics is that the particles that make up matter do not behave like tiny versions of the objects we encounter in daily life. They behave like both particles and waves simultaneously. This is not a metaphor. It is not an approximation or a convenient description. It is a precise, mathematical, experimentally verified feature of how quantum objects actually behave. When you set up an experiment to detect a particle, to pin down its location, it behaves like a particle. When you set up an experiment to observe its wave properties, its interference patterns, its spread through space, it behaves like a wave. The same object. Different experimental contexts. Fundamentally different kinds of behavior. The double-slit experiment demonstrates this with elegant brutality. Fire electrons one at a time at a barrier with two narrow slits, and let them land on a detector screen beyond it. After many electrons have passed, the pattern on the detector is not what you'd expect if electrons were tiny bullets, two bands corresponding to the two slits. Instead, you get an interference pattern, alternating bands of high and low detection probability, exactly as you'd see if you sent water waves through the slits. Each electron, passing alone, somehow interferes with itself, as though it were passing through both slits simultaneously. But if you place a detector at the slits to determine which one each electron actually passes through, if you observe the path, the interference pattern disappears. The electrons behave like particles again. The act of gathering the which path information removes the wave behavior. The quantum world is not strange because we haven't understood it well enough yet. It is strange because its strangeness is fundamental. The more carefully you look, the stranger it gets. Intimately connected to wave-particle duality is a principle that stands among the most profound discoveries in all of science. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that there is a fundamental limit to how precisely certain pairs of properties of a particle can be known simultaneously. The most famous pair is position and momentum. The more precisely you determine where a particle is, the less precisely you can know how fast it is moving and in what direction. The more precisely you know its momentum, the more spread out its possible position becomes. This is not a limitation of our instruments. It is not a problem that better technology will eventually solve. It is a feature of the mathematical structure of quantum mechanics, a consequence of what waves are and how they work. A wave with a perfectly definite position is an infinitely sharp spike, which requires an infinite range of frequencies to construct. A wave with a perfectly definite frequency, and therefore a perfectly definite momentum, is spread out infinitely in space. You cannot have both at once. The mathematics forbids it. The uncertainty principle means that particles do not have definite positions and momenta simultaneously. Not that we cannot measure them both at once, but that they do not both exist at once as definite values. The universe, at its fundamental level, is irreducibly fuzzy. It does not have the crisp, fully specified, every variable determined character that classical physics assumed. This connects directly to the quantum mechanical description of matter in terms of probabilities. At the quantum level, what physics describes is not the position of a particle, or its momentum, or its energy, but a mathematical object called a wave function, which encodes the probabilities of finding various values for these properties upon measurement. Before measurement, the particle does not have a definite position. It has a range of possible positions, each with an associated probability. Measurement selects one of those possibilities and actualizes it. What determines which possibility is actualized? As far as current physics can determine, nothing does. The outcome is genuinely random, not pseudo-random in the sense of being determined by hidden variables we haven't found, but irreducibly, fundamentally random in a way that appears to be built into the structure of nature. The universe, at its base, does not run on clockwork. It runs on probability. And this means that the past does not fully determine the future, not even in principle. Not because of any gap in our knowledge or any limit of our instruments, but because nature itself does not fully determine the future from the past at the quantum level. Strict determinism, the idea that the initial state of the universe plus the laws of physics completely fixes everything that will ever happen, appears to be false. The universe contains genuine openness. genuine contingency. Things that could have gone otherwise, and sometimes do. All of this leads to a picture of matter that is, when you step back from it, almost unrecognizable as a description of the familiar physical world. What quantum field theory, the most fundamental and most accurate physical theory we have, actually describes is not particles as tiny objects moving through space. It describes fields. Quantum fields, filling all of space, with different fields corresponding to different types of particles. An electron is not a small ball of stuff moving from place to place. It is an excitation of the electron field, a ripple, a vibration, a localized disturbance in an invisible medium that permeates the entire universe. Everything that exists, in this picture, is a vibration of a field. The photons carrying light. The quarks and gluons making up protons and neutrons. The electrons defining the chemistry of every atom. All of them are, in this most fundamental description, modes of excitation of underlying fields that have no color, no texture, no smell, no sound, nothing that maps onto any sensory property at all. The solid, colored, textured, substantial world of experience is generated by interactions between excitations of these invisible fields. The redness of an apple, the hardness of stone, the warmth of a fire, none of these properties exist in the fields themselves. They are what happens when those field excitations interact with a nervous system capable of constructing an experience from them. The world, at its most fundamental accessible level, is not made of stuff. It is made of process, of vibration, of interaction, of probability evolving through time according to equations whose solutions are not things but tendencies, likelihoods of outcomes, not the outcomes themselves. In the solid, stable, reliable world you navigate each day is an emergent phenomenon arising from the collective behavior of these tendencies, at scales large enough that the quantum uncertainties average out and the probabilistic becomes, for all practical purposes, predictable. The floor is solid. The table is real. The warmth of a blanket in the quiet of the night is genuine. And underneath all of it, at a level you will never directly experience and cannot directly imagine, the universe hums with something that doesn't quite have a name in any ordinary language. Something that is neither wave nor particle, neither solid nor empty, neither determined nor random in any simple sense. Something that generates, from its ceaseless invisible activity, the entire world of experience. The matter you are made of is not what it appears to be. It never was. The appearance is real, it is what is available to a body like yours, living at a scale like this, equipped with senses tuned to the macroscopic world. But beneath the appearance, the actual nature of what exists is something that physics can describe with extraordinary precision and that no human intuition, however trained or patient, was ever built to fully hold. There is a certain peace in that, if you let it in. The not knowing is not a failure. It is the appropriate response to something genuinely beyond the edges of ordinary thought. The universe is not obligated to be graspable. That it is as describable as it is, that the equations work, that the predictions hold, that any of this can be known at all, is itself something close to astonishing. Rest in the hum of it. The invisible fields, the probabilistic foundations, The electromagnetic force is keeping you precisely, perpetually, a breath away from everything you think you're touching. There is a question that quantum mechanics forces into the open, one that classical physics never had to confront seriously. If the properties of particles only become definite upon measurement, and if measurement is itself a physical process carried out by physical systems, then what, exactly, counts as a measurement? What makes an observation an observation? Does it require a conscious mind, or will any physical interaction do? And if any physical interaction counts, then why does the quantum world, with all its superpositions and probability clouds and fundamental fuzziness, give rise to the ordinary world we inhabit, a world where objects have definite positions, where cats are either alive or dead, where you and I agree on what we see? These questions sit at the unresolved heart of quantum mechanics. And they have been there since the beginning. One of the approaches that has emerged in recent decades to address this problem centers on a concept called relational observables. The idea, developed most fully by the physicist Carlo Rovelli, proposes that quantum states are not absolute. They are not properties that a system has independent of everything else. They are relational, defined only with respect to another physical system that interacts with them. In this view, there is no single universal wave function describing the state of everything from some imaginary view from outside. There is only the state of one system relative to another. An electron does not have a definite spin in some absolute sense. It has a definite spin relative to a measuring apparatus that has interacted with it. Another system that has not interacted with either the electron or the apparatus may consistently describe both as still being in superposition. This sounds like it should produce contradictions, different systems holding irreconcilable accounts of the same events. But Rovelli argues the mathematics shows this consistency is maintained, as long as you are careful about which facts are defined relative to which observers. The universe, in this picture, is not a collection of objects with absolute properties. It is a network of relationships, a web of interactions, with no view from nowhere and no absolute facts that float free of all physical context. Reality, again, is relational all the way down. Not approximately, not at the edges, but fundamentally, as a matter of what physics actually describes. Now, if quantum states are relational, if particles only acquire definite properties through interaction, a new question immediately arises. Why does the ordinary world look so definite? Why do we perceive objects with fixed positions and stable properties, rather than a shimmering fog of superposed possibilities? Why, when you and the person next to you both look at a table, do you agree on what you see, even though, at the quantum level, agreement is not automatically guaranteed? The answer, or at least a compelling candidate for one, is a process called quantum Darwinism. The idea was developed by the physicist Wojciech Zurek, and it draws on a striking parallel between biological evolution and the process by which quantum systems interact with their environments. In biological evolution, the environment selects for traits. Organisms whose characteristics are well suited to the environment survive and reproduce. Those that are poorly matched do not. Over time, the environment shapes the population. In quantum Darwinism, something analogous happens to quantum states. When a quantum system interacts with its environment, the surrounding air, the light bouncing off it, the electromagnetic field it generates, the environment effectively performs a continuous measurement on the system. The vast majority of possible quantum states are extremely fragile. They are rapidly disrupted by environmental interaction, their superpositions breaking down, their quantum interference erased. This process is called decoherence. Only certain states are robust. Only certain states survive repeated environmental interaction without being disrupted. These stable states, called pointer states, are the ones that persist. And crucially, they are the ones that leave redundant records throughout the environment. When you see an object, you are not receiving information directly from it. You are receiving photons that have bounced off it, each one carrying information about the object's state. Billions of photons are doing this simultaneously, each one independently encoding the same information about the same stable property, the object's position, its color, its shape. The environment acts as a vast copying machine, redundantly imprinting information about stable quantum states across countless independent channels. This is why observers agree. When you and another person both perceive the same table, you are both sampling different fragments of the same redundant environmental record. The information about the table's position has been copied into the light field, the air pressure variations, the electromagnetic fluctuations, so many times, and so many independent carriers, that independent observers sampling different fragments will all arrive at the same answer. Classical reality, in this picture, is not simply there waiting to be observed. It is the set of properties that the environment has selected for stability and copied redundantly enough that multiple observers can access consistent versions of it. It is, in a precise sense, the quantum world's answer to the question, what survives? This provides, for the first time, a physically grounded explanation for why the macroscopic world appears classical, why observers agree on what they see, and why the ordinary furniture of reality has the stubborn definite character it does, even though the underlying quantum world does not. The classical world is a consensus, not a human consensus. A physical one, enforced by the environment itself. And yet, the transition from quantum to classical still produces cases that resist tidy resolution. Cases where the logic of quantum mechanics, taken seriously, leads somewhere that ordinary intuition simply refuses to follow. Erwin Schrödinger, one of the founders of quantum mechanics, was deeply uncomfortable with the implications of the theory he helped create. In 1935, he constructed a thought experiment designed to expose what he saw as an absurdity at the heart of quantum mechanics. Imagine a sealed box containing a cat, a small amount of radioactive material, a detector, and a vial of poison. The radioactive material has a 50% probability of decaying within 1 hour. If the detector registers a decay, it triggers a mechanism that breaks the vial and releases the poison. If no decay is detected, the cat lives. According to the quantum mechanical description, before the box is opened, the radioactive atom is in a superposition of decayed and not decayed. The detector is in a superposition of triggered and not triggered. The vial is in a superposition of broken and unbroken. And therefore the cat, by the logic of quantum mechanics applied without restriction to macroscopic systems, should also be in a superposition of alive and dead simultaneously. Schrödinger intended this as a reductio ad absurdum. Cats are not in superpositions. The idea is, he felt, obviously ridiculous, and therefore something must be wrong with applying quantum mechanics unrestricted to the macroscopic world. But here is the strange thing. Decades of subsequent physics have not found the error Schrödinger was pointing to. Quantum superpositions have been demonstrated in increasingly large and complex systems, molecules, tiny mechanical resonators, systems containing trillions of atoms. The boundary between quantum and classical has proven stubborn to locate precisely. Decoherence explains why we never observe the cat in superposition. The interaction with the environment is so rapid and so thorough that the superposition breaks down almost instantaneously. But decoherence does not entirely resolve the question of why one outcome occurs and not another, or what, if anything, the superposition means before the box is opened. Schrödinger's cat is not a solved problem dressed in theatrical clothing. It is a genuine, unresolved tension between the mathematical formalism of quantum mechanics and the experienced reality of a world where cats are one thing at a time. And connected to this, though at a very different scale, is one of the deepest puzzles in modern theoretical physics. When matter falls into a black hole, what happens to the information it carries? Black holes, according to general relativity, are regions of spacetime where gravity is so extreme that nothing, not matter, not light, not any signal, can escape from within the event horizon. What falls and stays in? The information describing the detailed quantum state of the infalling matter seems to be lost forever. But quantum mechanics says this cannot happen. One of the most fundamental principles of quantum theory is that information is conserved. Physical processes can scramble information, redistribute it, make it practically inaccessible, but they cannot destroy it. The total information content of a closed quantum system is preserved over time. These two statements, general relativity's implication that black holes destroy information, and quantum mechanics' insistence that information is conserved, cannot both be entirely correct. One or both must be modified or reinterpreted. Stephen Hawking showed in the 1970s that black holes are not perfectly black. Quantum effects near the event horizon cause them to emit a faint thermal radiation, now called Hawking radiation, and to slowly evaporate over cosmological timescales. But the radiation appears to be thermal, carrying no information about the matter that fell in. If the black hole completely evaporates and all that remains is featureless thermal radiation, the information is gone. Whether this information is truly lost, or is somehow encoded in subtle correlations within the Hawking radiation, or escapes through some mechanism not yet understood, this is the black hole information paradox, and it remains one of the central open problems at the intersection of quantum mechanics and gravity. Resolving it likely requires a theory that unifies the two frameworks, a theory of quantum gravity, which we do not yet have. The information paradox is not an exotic edge case. It is a signal that our two deepest and most successful theories of physical reality are fundamentally incompatible in a way that has not yet been resolved, and that somewhere in the resolution, something we currently believe about the nature of information, space, time, or reality itself will have to change. Now step back from the cutting edge of physics and into the realm of thought experiments that have troubled philosophers for centuries. Problems not about particles or fields, but about identity, causation, and the structure of possibility itself. The grandfather paradox is perhaps the most famous paradox in popular thinking about time. Suppose time travel to the past is possible. You travel back in time and, for whatever reason, accident, or something more deliberate, you prevent your grandfather from meeting your grandmother. Your parents are never born. You are never born. But if you were never born, you could never have traveled back in time to prevent the meeting. And if you never traveled back, the meeting was never prevented, you were born, and the whole cycle repeats. The paradox is a closed causal loop that generates a contradiction. It seems to show that travel to the past is logically impossible, that a universe permitting it would immediately become incoherent. Physicists and philosophers have explored various responses. Some solutions propose that the timeline simply cannot be changed, that if you travel to the past, your actions are already part of the history that led to your existence. You cannot kill your grandfather because the fact that you are there means he survived. The past is self-consistent, and any attempt to change it already failed, already is recorded in the history that gave rise to you. Other solutions invoke parallel timelines. Your act of altering the past creates or branches into a different timeline, one where you were never born, but that timeline is separate from the one you came from. The paradox dissolves because the you who traveled back and the you who was never born are in different histories. Neither resolution is fully satisfying. Both raise new questions as fast as they answer old ones. The grandfather paradox remains a clean, uncomfortable demonstration that time, causation, and personal identity do not fit together neatly once you begin pulling at the seams. The ship of Theseus is an older puzzle, and in some ways a more intimate one. The ship of the legendary Greek hero Theseus was preserved as a monument. Over time, its planks rotted and were replaced, one by one, with new ones. Eventually, every single plank of the original ship had been replaced. Is the ship still the ship of Theseus? Most people feel, initially, that it should still count. The replacement was gradual, continuous. The ship never ceased being maintained and used. The identity persisted through the process of change. But then a second part of the puzzle is added. Suppose someone collected all the original planks as they were removed and reassembled them into a ship. Which one is the real ship of Theseus, the continuously maintained one, or the one made of the original material? This is not just a puzzle about ships. It is a puzzle about identity through time and change. And it applies, uncomfortably closely, to the human body, which replaces most of its cells over periods of years. The atoms that composed you a decade ago are largely gone. The matter has been exchanged. What makes you the same person you were then? Is it continuity of memory? Continuity of the physical process? Something about the pattern or the information rather than the substrate? The puzzle has no clean answer because identity, it turns out, is not a natural feature of the world that simply exists independently of how we choose to define it. It is a concept we apply to the world, and the world does not always respect the neat boundaries we draw. The Boltzmann brain is a stranger and more vertigo-inducing thought experiment, one that emerges directly from statistical mechanics and cosmology. The physicist Ludwig Boltzmann, working in the 19th century, developed the statistical understanding of thermodynamics, the idea that the behavior of gases and temperatures is the result of the collective statistical behavior of vast numbers of particles. In this framework, there is an extraordinarily small but non-zero probability that, purely by random thermal fluctuation, a collection of particles could spontaneously arrange themselves into any configuration, however improbable, including, in principle, a fully formed brain, complete with false memories of an entire life, momentarily fluctuating into existence in the void, experiencing a single moment of consciousness, and then dissolving back into chaos. If the universe is infinite in time, if it extends far enough into the future that even the most vanishingly improbable fluctuations eventually occur, then Boltzmann brains will eventually form, in arbitrary numbers. And if they form in sufficient numbers, they may vastly outnumber biological brains that form through ordinary cosmological and evolutionary processes. This leads to a troubling question. If you reason about what kind of observer you are most likely to be, and the answer is that most observers in an infinite universe are Boltzmann brains, momentary fluctuations with false memories, then should you conclude that you are probably one? That everything you remember is a fluctuation? That nothing you believe about the past is reliable? Most physicists take the emergence of this conclusion as evidence that something is wrong with the underlying cosmological model rather than as a genuine reason to doubt your own existence. A theory that predicts you are probably a momentary hallucination is probably not a correct theory. The Boltzmann brain paradox functions, in this sense, as a kind of consistency check, a reductio ad absurdum that reveals hidden problems in certain models of the universe's long-term evolution. But it also reveals something genuinely unsettling about the reach of probabilistic reasoning and the concept of infinity. In a truly infinite universe, with truly random fluctuations, almost anything happens somewhere, at some time. And reasoning about probability in an infinite setting leads quickly to conclusions that feel deeply, structurally wrong, even when the logic that produces them seems locally valid. Which is precisely what Hilbert's Hotel illustrates, in a different and more purely mathematical register. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on without end. Every room is occupied. A new guest arrives. Can they be accommodated? In a finite hotel, the answer would obviously be no. But the infinite hotel has a solution. Ask every current guest to move to the room with the next number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on, forever. Every guest has a new room, because for every number there is a next number. And room 1 is now empty. The new guest checks in. Now suppose an infinite number of new guests arrive simultaneously. Can they all be accommodated? Yes. Ask every current guest to move to the room whose number is double their current room number, room 1 to room 2, room 2 to room 4, room 3 to room 6. Every current guest is now in an even-numbered room. All the odd-numbered rooms, room 1, room 3, room 5, infinite in number, are now empty. The infinite new guests fill the odd rooms. A full infinite hotel can always accommodate more guests. Infinity plus 1 equals infinity. Infinity plus infinity equals infinity. These are not approximate statements or poetic exaggerations. They are precise mathematical facts about the behavior of infinite sets. Infinity does not obey the arithmetic of finite quantities. It is not a very large number. It is a different kind of thing entirely, and it behaves by different rules. The hotel paradox makes this visceral in a way that abstract mathematical statements sometimes do not. And it raises, quietly, a set of deeper questions. If space is infinite, if time is infinite, if the quantum multiverse is infinite, then the intuitions we use to reason about probability, uniqueness, and possibility may be systematically misleading. Infinitely many copies of you, making every possible decision, may exist somewhere in the structure of an infinite universe. Every possible history, every possible version of every event, may be actualized somewhere. The concept of what is rare and what is common, what is likely and what is not, becomes deeply unstable in the presence of true infinity. These paradoxes, the grandfather, the ship of Theseus, the Boltzmann brain, the hotel, are not merely intellectual curiosities. They are probes, each one testing the coherence of a concept we rely on: causation, identity, probability, quantity. And each one reveals that the concept, pushed to its limits, develops cracks. This is not a failure of human intelligence. It is a feature of the territory. The universe does not guarantee that its structure will be fully compatible with the intuitions of creatures who evolved to navigate a particular scale, a particular range of conditions, a particular corner of possibility. We are equipped for the middle distances. The very small, the very large, the infinite, the boundary between quantum and classical. These are places where our intuitions were never tested by evolutionary pressure, and where they sometimes lead us, very confidently, in the wrong direction. The paradoxes are signposts. They mark the places where ordinary thinking reaches its boundary and something else, something more careful, more humble, more willing to sit with unresolved tension, has to take over. And perhaps there is something restful in that recognition, as strange as it sounds. The edges of understanding are not places of failure. They are the most alive part of the map. They are where the questions are still open, still genuinely undecided, still waiting for someone patient enough to sit with them without demanding that they resolve. The night is a good time for that kind of patience. When the ordinary certainties have gone quiet, and the mind is soft enough to hold a paradox without needing to immediately solve it. Let the infinite hotel stand full and empty at once. Let the cat be what it is. Let the information fall, and trust that somewhere in the mathematics of a theory not yet written, it is not lost. Some of the most disorienting discoveries are not the ones that reveal the universe to be vast or strange or mathematically complex. Some of the most disorienting discoveries are the ones that show you that your intuition about something perfectly ordinary, something you have encountered hundreds of times, was quietly wrong all along. The birthday paradox is one of those. How many people need to be in a room before there is a better than 50% chance that two of them share the same birthday? Most people, when they first encounter this question, reach for an answer somewhere in the hundreds. A year has 365 days. Surely you need a substantial fraction of that before the odds favor a match. The actual answer is 23. In a group of just 23 people, there is a greater than 50% probability that at least two of them share a birthday. By the time you reach 70 people in a room, the probability is over 99%. Near certainty, in a group that could fit comfortably around a large dinner table. The reason this feels so wrong is that we instinctively compare each new person to ourselves. We think, what are the chances that someone in this room shares my birthday? And for that question, you really would need a large group. But the paradox asks a different question. It asks whether any two people among the group share a birthday, any pair, from the enormous number of possible pairs that exist within even a modest group. In a group of 23 people, there are 253 distinct pairs. Each pair has roughly a 1 in 365 chance of sharing a birthday. When you account for all of those chances simultaneously, the cumulative probability climbs far faster than intuition suggests. The birthday paradox is a vivid demonstration of how poorly the human mind handles combinatorial growth, the way the number of possible connections in a group expands much faster than the group itself. It is why social networks saturate so quickly, why diseases spread faster than they seem like they should, why coincidences in general occur far more often than we expect. We undercount the connections. We think linearly when the reality is multiplicative. And then there is the Mpemba effect, which belongs to a different category of surprise entirely, not mathematical, but physical, and in some ways even more counterintuitive because it concerns something as mundane as hot and cold water. In 1963, a Tanzanian schoolboy named Erasto Mpemba noticed something while making ice cream. Hot milk, placed in the freezer alongside cold milk, froze first. He brought this observation to his physics teacher, who dismissed it. He brought it later to a visiting physicist named Dennis Osborne, who took it seriously enough to investigate. The effect was confirmed experimentally. Under certain conditions, hot water freezes faster than cold water starting at the same conditions. This should be impossible by naive reasoning. Cold water has less thermal energy to lose before reaching freezing point. Hot water has more ground to cover. It should always take longer. And yet the effect has been observed and reproduced, though it is not universal. It depends on the containers, the volumes, the humidity, the specific starting temperatures, and a range of other conditions that make it somewhat finicky to demonstrate reliably. The explanations that have been proposed include evaporation reducing the mass of the hot water sample, differences in dissolved gas content between hot and cold water, convection patterns forming differently in hot water and accelerating heat loss, and differences in the structure of water at different temperatures affecting how efficiently it transfers heat. No single explanation has been universally accepted. The Mpemba effect remains, in a quiet way, an open question in the physics of everyday substances, a reminder that water, the most abundant liquid on Earth's surface, the substance that makes up the majority of your body, a thing so common it is used as a synonym for ordinary, is not fully understood. Not completely. Not even now. The ordinary world contains more mystery than it admits. Now shift scales entirely. From kitchen physics to forest ecology. From the counterintuitive to the quietly astonishing. Beneath every forest floor, invisible and largely unnoticed, there is a network. Trees do not stand alone. Their roots connect, indirectly and sometimes directly, to the roots of neighboring trees through a dense web of fungal threads called mycorrhizae. These fungi grow in intimate association with root systems, extending the reach of the roots enormously, accessing water and nutrients from a far larger volume of soil than the roots could reach on their own. In exchange, the tree provides the fungus with sugars produced through photosynthesis. But the network does more than connect each tree to the soil. It connects trees to each other. Through this fungal web, trees pass carbon, nitrogen, water, and chemical signals back and forth. Older, larger trees, sometimes called mother trees by researchers studying this phenomenon, have been shown to send disproportionate amounts of carbon through the network to younger seedlings growing in shade, where photosynthesis is limited. Trees under attack from insects or pathogens release chemical signals that travel through the network and prime the defenses of neighboring trees before the threat reaches them. The forest is not a collection of individual organisms competing for resources in isolation. It is a community, connected by a shared infrastructure, capable of something that looks, functionally, very much like mutual support. The language of competition that dominated ecological thinking for much of the 20th century turns out to be incomplete. Cooperation, interdependence, and collective behavior are as fundamental to forest ecology as competition. And the system exhibits coordination at a scale that is difficult to explain purely through local interactions. When a forest is stressed, by drought, by disease, by damage to its canopy, the network responses can involve trees across large areas, adjusting their behavior in ways that suggest sensitivity to the condition of the system as a whole. Individual trees die, but they release their stored carbon and nutrients into the network as they do, passing resources to their neighbors in a last redistribution that benefits the community they are leaving. A forest, looked at this way, begins to resemble less a collection of separate things and more a single distributed organism, or at least something that sits provocatively close to that boundary, in a way that challenges the concept of individuality itself. The story of life on Earth is longer than the human mind finds easy to hold. And deep in that history, there is a detail that reframes the familiar image of a blue and green planet in an unexpected way. For most of Earth's history, the dominant color of life may not have been green. Chlorophyll, the pigment responsible for the green of plants, absorbs red and blue light and reflects green. But some researchers have proposed that an earlier and perhaps once dominant form of photosynthesis used a pigment called retinal, which absorbs green light and reflects red and purple. If microbial life using retinal-based photosynthesis was as widespread on early Earth as chlorophyll-based life became later, the planet's surface would have appeared strikingly different to any observer from space. Not green, but purple. This is sometimes called the purple Earth hypothesis. It remains speculative, and the evidence is indirect. but it points to something worth pausing on. The green of the living world, which feels as fixed and natural as anything in our environment, is a product of a particular biochemical solution to the problem of capturing light. A different solution, equally viable, produces a different color. The world we know is one outcome among several that were chemically plausible. Life colored the earth, and could have colored it differently. Animals sense the world in ways that consistently exceed what human perception can easily imagine. We have already considered the bee's ultraviolet and the dog's olfactory landscape. But there are modes of perception that go further still into territory that has no parallel in human experience. Snakes, particularly certain species of pit vipers and pythons and boas, possess specialized sensory organs capable of detecting infrared radiation, heat, with sensitivity fine enough to form something approaching a thermal image of their surroundings. This alone is remarkable. But there is evidence suggesting that some snake species can also detect seismic vibrations with unusual sensitivity, responding to ground movements that precede earthquakes in ways that have attracted genuine scientific interest. Before certain earthquakes, unusual animal behavior has been reported, and snakes emerging from dormancy, moving in large numbers, or behaving in agitated and atypical ways have been among the most consistently documented observations. The mechanisms are not fully understood. Snakes have no external ears in the conventional sense, but they are exquisitely sensitive to ground-borne vibration through direct contact with the surface. Whether this sensitivity constitutes something like earthquake prediction, or is simply a response to early and subtle ground motion that instruments in the same area also record, the practical result may be similar. China has experimented with snake behavior monitoring stations as part of earthquake early warning research, tracking the behavior of snake populations in real time and watching for the anomalies that have, in some documented cases, preceded seismic events. The living world is an instrument of geophysical sensing. The snake is a seismograph. There is a small, almost trivial-seeming physical response that the human body produces, to cold, to fear, to certain music, which turns out, on closer inspection, to carry an unexpected biological secret. Goosebumps are the visible result of tiny muscles at the base of each hair follicle contracting, pulling the hair upright. In other mammals, this serves a clear purpose. It makes the fur stand up, trapping more air and providing better insulation, or making the animal appear larger to a threat. In humans, who have largely lost their body hair, the response is mostly vestigial, a reflex that no longer serves its original purpose, surviving as a kind of evolutionary memory. But recent research has revealed something unexpected about those same tiny muscles. The stem cells that sit in the hair follicle and are responsible for hair regeneration are directly connected to the nerve endings and muscle tissue associated with the goosebump response. When those muscles contract repeatedly, stimulated by cold or the nerves associated with stress, they appear to activate the stem cells, promoting hair growth. The same ancient reflex that makes your arms prickle when you hear a piece of music that moves you is also, quietly, participating in the maintenance and regeneration of your hair follicles. A response that looks like a useless leftover from our furred ancestors turns out to be functionally entangled with the ongoing biology of the body in ways that were invisible until recently. Nothing in biology is ever entirely vestigial. The body repurposes, retasks, rewires. What appears to be an evolutionary remnant is often still doing something, even if what it's doing has quietly shifted over millions of years. Here is a fact about cancer that seems, at first, like it should be straightforwardly false. Larger animals do not get more cancer than smaller ones. In fact, across species, there is essentially no correlation between body size and cancer rate, even though larger animals have vastly more cells, and each cell division carries some small probability of a cancerous mutation. A blue whale has roughly 1,000 times more cells than a human being. By naive expectation, it should have a cancer risk orders of magnitude higher. But blue whales do not appear to die of cancer at dramatically higher rates than humans. Elephants, with roughly 100 times as many cells as a human, have cancer rates significantly lower than humans. This is known as Peto's paradox, named after the epidemiologist Richard Peto, who first clearly articulated it. The resolution lies in evolution. Large, long-lived animals have had strong evolutionary pressure to develop more robust cancer suppression mechanisms. Elephants, for example, have been found to carry multiple copies of a tumor suppressor gene called TP53, a gene that in humans exists in just one copy and whose malfunction is implicated in roughly half of all human cancers. The elephant genome appears to have accumulated additional copies of this protective gene over evolutionary time, providing redundant layers of cancer defense that compensate for the increased cell number. Large body size and long lifespan create selection pressure for better cancer suppression. The organisms most exposed to the risk have evolved the most sophisticated defenses against it. The vulnerability and the protection evolved together. And there is a final detail from the natural world that brings us back to the ocean, not its deep floor, but its living inhabitants, and one of the most specialized physiological achievements in the animal kingdom. Sperm whales dive deep. Very deep. They regularly descend to over 1,000 meters in pursuit of squid, and have been recorded at depths approaching 3,000 meters, in complete darkness, under crushing pressure, where the water temperature is only a few degrees above freezing. These dives can last over 90 minutes on a single breath. The physiological adaptations that make this possible are extensive and extraordinary. Sperm whales have blood that carries oxygen far more efficiently than human blood, with a much higher concentration of hemoglobin and myoglobin, the proteins that bind and store oxygen in blood and muscle respectively. During a deep dive, their heart rate slows dramatically. Blood is redirected away from peripheral tissues and concentrated in the brain, heart, and essential organs. Their spleens, which store a reservoir of oxygenated blood cells, contract and release that reserve into the circulation at the start of the dive. Their chests are flexible enough to compress under deep pressure without injury, unlike the rigid human ribcage. And their muscles are so densely packed with myoglobin, the molecule that stores oxygen in muscle tissue, that sperm whale muscle is nearly black in color. 90 minutes in the dark, 3,000 meters below the surface, on a single breath, hunting by echolocation in absolute silence. The whale surfaces, breathes, and dives again. the natural world does not exhaust its inventiveness at the visible surface. The deeper you look, at fungal networks threading through forest soil, at the molecular machinery of cancer suppression, at the sensory systems of creatures whose perceptual worlds have no human equivalent, the more clearly it becomes that life is not simply present on this planet. It is woven into it, shaped by it, continuously reshaping it in return. Every organism is a solution to a set of physical and ecological problems, worked out over timescales that dwarf human history, refined by a process that never stops. We are embedded in that process. We are part of it. The same evolutionary pressure that gave the elephant its redundant tumor suppressors and the whale its oxygen-storing muscle shaped the brain that is now, quietly, in the late hours, turning these facts over, finding them strange, finding them beautiful, wondering what they add up to. They add up, perhaps, to this. The world is far more connected, far more alive, far more ingeniously organized than the surface of things suggests. The network runs everywhere. Through the forest floor and the whale's blood and the quantum fields and the curved space-time above the Earth's surface. Everything is in relation to everything else. And you, right now, in the stillness, are part of that relation. Not an observer looking in from outside. A thread in the fabric, resting for a moment, breathing quietly, as the whole enormous interconnected thing continues, in its unhurried way, to be. Greenland sharks are among the least known large animals on Earth, which is remarkable given their size. They can reach lengths of over 6 meters, making them among the largest carnivorous sharks in the ocean. They live in the cold, deep waters of the North Atlantic and Arctic, moving through the darkness at depths that make observation extremely difficult. For a long time, almost nothing was known about their lives. And then researchers began to examine their ages. Greenland sharks grow extraordinarily slowly, less than a centimeter per year. Because they lack the calcified tissues that are used to age most other sharks, scientists turn to radiocarbon dating of proteins in the lens of the eye, tissue that forms before birth and is never replaced. The results were extraordinary. The oldest Greenland shark in the study was estimated to be approximately 400 years old. The margin of error was large. The estimate ranged from roughly 370 to 500 years. But even the lower bound places the animal's birth somewhere in the 17th century. A shark alive today may have been born before Isaac Newton formulated the laws of motion, before the telescope transformed our understanding of the cosmos, before most of the political map of the modern world existed in anything like its current form. It moves through the Arctic deep, slowly, as it has always moved. Cold-blooded, unhurried, ancient in the most literal sense. The 400-year human story of science and industry and transformation is, from the perspective of a Greenland shark alive through all of it, simply the duration of a single life. There is no evidence that Greenland sharks experience time the way we do, or that they register the passage of centuries as anything other than the continuation of existing. But there is something in that image, a creature alive across the entire span of modern human history, unaware of and unmoved by any of it, that quietly reframes the scale of things. Now here's a small, curious fact about the animal most likely to be somewhere nearby as you listen to this. domestic cats do not meow at each other. Adult cats communicate with other adult cats primarily through scent, body posture, facial expression, and a range of vocalizations that include chirping, chattering, trilling, hissing, and growling. But the meow, that particular sustained vocalization that most cat owners consider the primary sound of their pet, is used by adult cats almost exclusively in communication with humans. Kittens meow to their mothers. But as cats mature, that vocalization largely drops out of cat-to-cat communication. What researchers believe happened is that domestic cats, over roughly 10,000 years of living alongside humans, effectively retained and elaborated a juvenile vocalization because they discovered it worked. Humans respond to it. Humans who responded attentively to meowing cats were, presumably, better at providing food and care. The cats that meowed to humans thrived. The meow is, in a sense, a communication system that cats develop specifically for us. Each cat appears to develop a somewhat individualized repertoire of meow sounds, varying in pitch, duration, and urgency, tuned over time to the specific responses of the specific humans they live with. Your cat's meow is not a generic cat sound. It is, in a modest but real sense, a language developed between that particular animal and the particular people in its household. The relationship between domestic cats and humans is usually described as a human decision. We domesticated cats, or at least tolerated their presence near grain stores until they became companions. But the communication dimension of that relationship was shaped by the cats as much as by the humans. They learned us, too. Now shift from the living world to a question about identity, organization, and what it means for two things to be the same. Identical twins begin as a single fertilized egg. They share virtually all of their DNA, not approximately the same, but genuinely, almost completely identical at the genetic level. They develop in the same womb, exposed to the same maternal environment, the same hormonal signals, the same nutrition. By any standard definition, they are as biologically similar as two separate human beings can possibly be. And yet their fingerprints are different. Not dramatically different, they share the same general pattern type, the broad category of loop or whorl or arch that runs in families. But the specific ridge details, the precise contours that make a fingerprint unique, diverge. No two people on Earth have the same fingerprints, including identical twins. The reason is that fingerprint formation is not directly encoded in DNA. The ridges form during fetal development in response to the physical pressures and movements of the developing fingers, the way the skin buckles and folds under growth stress, the exact position of the fingers in the womb at particular developmental moments, local variations in the fluid environment surrounding the hand. These are not genetic instructions being executed. They are physical processes responding to conditions that vary minutely and unpredictably from finger to finger, from moment to moment, from one twin to the other even within the same womb. The environment shapes the body in ways that genetics does not fully determine. And this is not limited to fingerprints. Identical twins raised together show differences in height, weight, disease susceptibility, and a wide range of other physical traits that emerge from the accumulation of different environmental exposures, different developmental accidents, different life experiences imprinted on the body at a molecular level. This goes deeper than most people realize. Epigenetics, the study of changes in gene expression that do not involve changes to the DNA sequence itself, has revealed that the environment continuously modifies how genes are read. Chemical tags are added to or removed from DNA, turning genes up or down in response to stress, diet, exercise, sleep, temperature, and a vast range of other inputs. These modifications can persist. They can, in some cases, even be passed to subsequent generations. The body you have is not simply the body your genes specified. It is the body your genes produced in dialogue with every environment you have moved through: the womb, the childhood home, the climate, the diet, the stress, the sleep, the accumulated physical history of a specific life lived in a specific way. Two people with identical genomes will build somewhat different bodies if they live different lives. The blueprint is shared. The building is not. This means that no two human beings are truly identical, not even those who start from the same genetic material. Every human body is a unique physical object, shaped by a combination of genetic instruction and environmental contingency that has never occurred before and will never occur again in quite the same configuration. This is easy to say and strangely easy to not fully feel. We speak of human biology in general terms, of the human body as a type, as though there were a standard version and individuals were instances of it. But the individual is primary. The general description is an abstraction. Every specific human body is its own thing, distinct, unrepeatable, shaped by a history that belongs to no one else. Flamingos are born with gray or white feathers. The vivid pink that makes them immediately recognizable is not genetic. It is dietary. Flamingos feed extensively on algae and small crustaceans that are rich in carotenoid pigments, the same family of compounds responsible for the orange of carrots and the red of tomatoes. These pigments are processed in the flamingo's liver and deposited in the feathers and skin during molting. The more carotenoid-rich the diet, the deeper the pink. Flamingos in captivity, unless their diet is supplemented with appropriate pigments, fade to near white. The flamingo's color is not what it is. It is what it eats, made visible. The body is a display of its inputs, which connects to a detail about the human body that tends to produce a particular kind of surprised pause when people first encounter it. The human body is made of chemical elements: carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus, and smaller amounts of many others. These elements are real, physical, purchasable substances. And if you were to source all the elements present in an average adult human body in their pure forms, at current market prices, accounting for the more exotic trace elements, the vanadium, the molybdenum, the small quantities of rare earth elements that appear in biological systems, the total comes to a figure in the range of $160,000, or roughly equivalent in pounds sterling. Some estimates place this higher, particularly when accounting for elements present in tiny quantities that are nevertheless expensive to isolate and purify. The figure is not trivial. The raw material of a human being is genuinely valuable. And yet if you simply purchase those elements in bulk, without the elaborate biological organization that structures them, just the atoms, in their elemental or common compound forms, the cost would be only a small fraction of that. Bulk carbon, bulk hydrogen, bulk oxygen. A few tens of dollars. Perhaps less. The difference between a handful of common chemicals and a living human being is not the material. It is entirely the organization. The sequence in which the molecules are arranged. The way proteins fold into precise three-dimensional shapes that enable them to catalyze specific chemical reactions with extraordinary efficiency. The regulatory networks that read the genome and translate it into a continuous, self-maintaining biological process. The nested hierarchy of organization from atoms to molecules to organelles to cells to tissues to organs to systems to the whole coordinated living entity. All of that, the organization, the structure, the functional architecture, is what the value is. Not the stuff. The arrangement of the stuff. This is a principle that reaches far beyond biology. It is, in a sense, a fundamental truth about what value means in a physical world. Raw materials are relatively abundant and relatively cheap. Organization is rare, difficult to produce, and extraordinarily powerful. A pile of sand and a silicon chip contain overlapping material, but one of them can run calculations that would have seemed magical a century ago. The difference is purely structural. Life is the universe's most elaborate demonstration of what organization can do with ordinary materials. And the human body is, by any measure, among the most intricate organizational achievements in the known cosmos, built from the most common elements in the universe, assembled by a process that took 4 billion years to develop, capable of experiencing music and grief and curiosity and the strange pleasure of learning something that reframes everything else. Now here is something that is true about your body right now, in this moment, that you have almost certainly never been told. You are glowing. Not metaphorically. Not in any spiritual sense. Literally. The human body emits light, actual photons, in the visible spectrum, as a byproduct of metabolic processes. The emission is extraordinarily faint, roughly 1,000 times weaker than the threshold of human vision, which is why you cannot see it and have never noticed it. It was first clearly demonstrated using highly sensitive photon-detecting equipment in studies conducted in Japan in the late 2000s. Researchers placed human subjects in completely darkened rooms and used cameras capable of detecting single photons over long exposure periods. The results showed that the human body emits a faint glow that fluctuates over the course of the day, strongest in the late afternoon and weakest in the early morning. Detecting single photons over long exposure periods. The face, particularly the cheeks and forehead, appears to emit somewhat more light than other areas of the body. The light is believed to arise from biophoton emission, photons released as a byproduct of oxidative metabolic reactions, the same fundamental chemistry that powers cellular activity throughout the body. As molecules are broken down and rebuilt, electrons transition between energy states, and some of those transitions release photons. The process is continuous and is happening in every living cell. Every living thing emits light in this way. Trees, bacteria, animals, all of them glow faintly in the dark, their metabolic activity casting a light too dim for any biological eye to detect. You have never seen yourself as you physically are. The visible human body, the one that appears in mirrors and photographs, is the body illuminated by external light. The body as it actually exists in darkness is something else, a faintly self-luminous form, fluctuating with the rhythms of metabolism, emitting its own quiet light into the surrounding dark. There is something about this that feels, even at this purely physical level, like it connects to something larger. The metaphors of light that appear across so many human traditions, the association of consciousness with illumination, of life with brightness, may have a physical substrate that those traditions could not have known about but intuited nonetheless. Or perhaps the connection runs the other way. Perhaps the fact that living things actually, physically glow was never needed to justify the metaphor, because the metaphor points at something that the physical fact only partially captures. Either way, here is what is literally true. In the quiet of this moment, in whatever dark room or still space you are in, you are producing light. Not much. Not enough to see by. But real photons, real electromagnetic radiation in the visible spectrum, leaving your body and traveling outward into the space around you. The universe is a little brighter for your being in it. In the most precise, physical, measurable sense of the word. There is a version of reality that we carry around without examining it, a set of background assumptions so thoroughly absorbed that they don't feel like assumptions at all. They feel like the world. And then along comes a small, unexpected fact, apparently trivial, and something in the picture shifts. Here is one. A solid glass ball, dropped onto a hard surface, will bounce higher than a rubber ball of the same size. Not slightly higher. Significantly higher. A high-quality glass ball can return to nearly its original drop height, while a rubber ball, the material most people associate with bounciness, with elasticity, with the very concept of a bouncy object, loses considerably more energy on impact. The reason is that rubber deforms significantly on impact and then springs back, but the deformation process itself dissipates energy as heat. Glass, being far more rigid, barely deforms at all. The collision is almost perfectly elastic, energy goes in, and energy comes almost entirely back out, with very little loss to internal friction or heat. The ball returns to nearly where it started. Everything you thought you knew about what makes something bouncy turns out to be more specific and more interesting than the simple story suggested. The softness that seems like it should help is actually working against the bounce. The hardness that seems like it should prevent bouncing is precisely what enables it. Small facts like this are doors. They open onto larger questions about the nature of materials, about what we mean by elasticity, about how deeply our intuitions about physical properties are shaped by everyday experience rather than careful examination. And then there's a fact that takes a sharp turn from the physics of glass balls into the physics of the human body, specifically, something that happens several dozen times a day and which everyone does and no one discusses. A human fart travels at approximately 7 miles per hour. This is a real measurement, from actual research, and it belongs in a discussion about reality and perception because it illustrates something genuinely interesting about the gap between subjective experience and physical fact. The gas exits the body at speed, disperses rapidly into the surrounding air, and the molecules responsible for the odor diffuse outward in a plume shaped by air currents and convection. The combination of the initial velocity, the diffusion rate, and the sensitivity of the human nose to certain sulfur compounds at extraordinarily low concentrations is why a room can be affected so quickly and so thoroughly. The olfactory system can detect some odor molecules at concentrations of parts per trillion. It is, in some respects, one of the most sensitive detection instruments in the natural world. The fact that something as unremarkable as a digestive byproduct can travel a measurable distance at a measurable speed and activate a sensor capable of parts per trillion detection, this is a small window into the extraordinary precision hidden inside the apparently ordinary. Inside the ear, there are 3 bones that are the smallest bones in the human body. They are called the malleus, the incus, and the stapes, the hammer, the anvil, and the stirrup, and together they form a mechanical chain that bridges the eardrum and the fluid-filled cochlea of the inner ear. When sound waves arrive at the eardrum, they set it vibrating. Those vibrations travel through these 3 tiny bones, and the mechanical arrangement of the chain, the leverage geometry of the linkage, amplifies the pressure of the vibration before it reaches the inner ear. The amplification is not enormous by electronic standards, but it is precisely calibrated to the frequency range of human speech and the sounds most relevant to human survival and communication. The middle ear is a mechanical amplifier tuned by millions of years of evolution to the particular frequencies that mattered most to the creatures that needed to hear them. 3 bones, the largest of which is about the size of a grain of rice, doing the quiet mechanical work that makes conversation possible. The body is full of engineering of this kind, solutions to physical problems, arrived at through evolutionary time, that turn out to be elegant in ways that only become visible when you look closely enough to see the problem being solved. Here is something about your eyes that surprises almost everyone who hears it. Your eyes are the same size now as they were when you were born. Almost every other organ in the body grows substantially between birth and adulthood. Bones lengthen. Organs increase in mass. The brain grows significantly in volume during the first years of life. But the eyeballs themselves are nearly full-sized at birth, already approximately 2/3 of their adult diameter, and reach their adult size by early childhood, long before the rest of the body catches up. This is why babies' eyes look so large relative to their faces. They are not disproportionately large. They are close to adult size, in a face that has not yet grown to match them. As the face grows around the eyes over childhood and adolescence, the eyes come to look proportionate, not because the eyes have grown, but because everything else has. What does grow, and grows throughout life, are 2 other features of the face. The nose and the ears continue to increase in size across adulthood, slowly and continuously, long after growth in most other parts of the body has stopped. The mechanism is primarily the ongoing effects of gravity on connective tissue. Cartilage, which makes up the structural core of both the nose and the ears, is not rigid bone. It is flexible, and over decades it responds to gravity by gradually elongating. The skin and soft tissue surrounding it follow. The result is that a person's nose and ears in old age are measurably larger than they were in middle age, which in turn were measurably larger than in youth. This slow, continuous, gravity-driven change is one of the reasons faces look different in old age in ways that go beyond wrinkles. The proportions have genuinely shifted. The face has been, very gently and over a very long time, reshaped by the same force that governs the motion of planets. Gravity leaves its mark on everything. Even cartilage. Even the face you see in the mirror. Honey found in ancient Egyptian tombs, sealed for over 3,000 years, has been found to be perfectly edible. This is not legend. Archaeologists have reportedly tasted it. 3,000-year-old honey, and it remained what it was: sweet, thick, biologically stable. The reason honey is effectively immune to spoilage comes down to chemistry. Honey has extremely low water content, typically below 18%, which means bacteria and microorganisms cannot grow in it because there is not enough moisture to support their metabolism. It is also highly acidic, with a pH that further inhibits microbial activity. And bees add an enzyme to honey during its production that generates small amounts of hydrogen peroxide, a natural antibacterial compound. The combination of low moisture, high acidity, and hydrogen peroxide creates an environment where almost nothing biological can survive long enough to break the honey down. Seal it for moisture, and it will simply remain as it is, essentially indefinitely. 3,000 years ago, someone kept bees in Egypt. The flowers they visited, the nectar they gathered, the chemical transformation that happened inside the hive, that process produced something that time could not touch. The world changed entirely around it, and the honey waited, stable and sweet, to be found. Now here's a geographical fact that, once you look at a map with it in mind, seems both obvious and strangely overlooked. The overwhelming majority of Earth's human population lives in the Northern Hemisphere. Approximately 90% of all humans alive today live north of the equator. The Northern Hemisphere contains the majority of Earth's total land area, about 68%, and that land includes the large, densely populated continental masses of Asia, Europe, and North America. The Southern Hemisphere is dominated by ocean, with South America, Sub-Saharan Africa, and Australia representing the primary landmasses, and all three have lower population densities than their northern counterparts. The result is a planet whose human story is, geographically, almost entirely a northern story. The great ancient civilizations, Mesopotamia, Egypt, the Indus Valley, China, all northern. The major centers of population today, China, India, Europe, the eastern United States, all northern. The experience of the planet as a human place is an experience of roughly 1/2 of a sphere, biased heavily toward one pole. Which means that for 90% of humanity, the sun travels through the southern part of the sky. Summer is June, July, and August. The seasons and their associations, the cultural meanings layered onto spring, autumn, the particular quality of winter light, are northern meanings. When those associations travel south in literature or film or music, they arrive as borrowed references, shaped by a climate and a sky that most of the people consuming them have never experienced. Humanity is a northern species, on a planet that didn't have to be arranged that way, living inside a set of cultural assumptions shaped by which side of the equator most people happen to have ended up on. Oxford University was founded in the late 11th or early 12th century. Teaching there was already established and documented by 1096, and the university took recognizable institutional form during the 12th century. It is among the oldest continuously operating universities in the world, a place where people have been teaching and learning in an unbroken institutional tradition for nearly 1,000 years. The Aztec Empire, the vast Mesoamerican civilization centered at Tenochtitlan in the Valley of Mexico, was founded in 1428. Oxford University is older than the Aztec Empire. This is the kind of historical juxtaposition that reorders the way things feel in time. The Aztecs tend to occupy a mental category of the ancient past, a pre-Columbian civilization of pyramids and ritual and vast urban complexity that feels as though it must belong to a deep historical era. Oxford, by contrast, is still operating, still producing graduates, its buildings still standing in a recognizable English city. It feels present, contemporary, part of the continuing world. But the numbers say something different. By the time the Aztec Empire rose to regional dominance in central Mexico, Oxford had already been educating students for 3 centuries. The seemingly ancient and the seemingly contemporary are not where intuition places them. The timeline of human civilization does not sort neatly into the alive and the past based on what has survived and what has not. And now here is a number that defeats imagination rather than intuition, because imagination simply does not have the tools to hold it. The number of possible distinct chess games, the number of different sequences of moves that can be played in a game of chess, is estimated to be around 10 to the power of 120. This is a number so large that it is given its own name, the Shannon number, after the mathematician Claude Shannon, who estimated it in 1950. For comparison, the estimated number of atoms in the observable universe is approximately 10 to the power of 80. The Shannon number is larger than the number of atoms in the observable universe by a factor of roughly 10 to the power of 40, itself an incomprehensibly large number. A game of chess is played on a board 8 squares by 8. Each piece moves according to simple rules. The total number of pieces is 32. And from these modest physical ingredients, the number of possible distinct games exceeds the number of atoms in everything we can observe by 40 orders of magnitude. Complexity does not require a large physical scale. It requires combinatorial depth. It requires the right kind of structure, the right set of interacting rules, to generate a space of possibility that expands faster than any physical quantity we can measure. Chess is 32 pieces on 64 squares. And it contains more possibility than the observable cosmos contains matter. What this says about the nature of information, about the relationship between simple rules and emergent complexity, about the kind of universe that could generate both chess and the mind that plays it, these are questions worth carrying quietly into sleep. Now, let the pace slow a little. Let the facts become more contemplative. Because what follows is less about individual surprising truths and more about the nature of time itself, experienced from multiple angles, at multiple scales. You will spend approximately 1/3 of your life asleep. For an 80-year life, that is roughly 26 years. Not dozing, not resting, genuinely, deeply asleep. Unconscious. Experiencing, at most, a handful of hours of dreams out of every 24. For 26 years, the world will continue without your participation, and your body and brain will be doing something that science has studied for decades and still does not fully understand. Sleep is not passive. It is an active process involving complex cycles of neural activity, hormonal regulation, memory consolidation, cellular repair, and immune maintenance. The brain during certain stages of sleep is nearly as active as during waking, doing things that cannot be done while conscious, reorganizing memories, clearing metabolic waste products, resetting emotional tone, maintaining the biological systems that waking life depends on. A life without sleep would end within weeks. Sleep is not a suspension of life. It is one of the forms life takes, perhaps the most intimate and least examinable one. The sleeping self is still you, still doing the work of being alive, in a mode of existence you have almost no access to from the waking side. 1/3 of your life in that other mode. A quarter of a century, roughly, in the dark interior of a consciousness turned inward on itself, doing something essential that it will never fully report back. We have already spent time with the Greenland shark, that ancient, slow-moving creature of the Arctic deep whose lifespan can span 4 centuries. But it's worth returning to that image in the context of time itself, because the shark's existence says something about the relationship between the pace of living and the experience of duration. For a cold-blooded animal living in near-freezing water, metabolic rate is extremely low. Every biological process proceeds slowly. Heart rate is low. Digestion is slow. Growth is slow. The cellular turnover that marks the passage of time in warm-blooded animals, the continuous replacement of cells, the ongoing expenditure of energy, happens at a fraction of the rate it does in a mammal. Does a slow metabolic rate mean a different subjective experience of time? We cannot know from the inside. But it raises a question about what duration means for different kinds of organisms. A mayfly lives for a single day in its adult form, but that day may be, in terms of neural events processed, in terms of actions taken and responses made, as full and complete as a much longer period in a slower animal. Time as a biological experience may not map straightforwardly onto time as a physical measurement. The Greenland shark's 4 centuries may not feel like 4 centuries from inside whatever experience it has. Or they may feel like much more. We don't know. What we know is that the physical substrate of its life is operating at a pace so different from ours that any direct comparison of what time means to it and what time means to us is built on an assumption we cannot verify. Whales, which we have visited before in the context of their deep diving, add another dimension to this question. They are large, long-lived, cognitively complex animals living in a medium that transmits sound very differently from air. Whale song travels hundreds and sometimes thousands of miles through the ocean. The social and acoustic world of a whale operates at spatial scales that have no human equivalent. A blue whale perceiving a low-frequency sound from another blue whale hundreds of kilometers away is operating in a relational geography of time and space that we can describe mathematically but cannot directly imagine. Whether this means whales experience duration differently than we do is genuinely unknown. But the question of whether the pace of experience, the felt texture of time passing, is the same for all conscious creatures seems increasingly unlikely to have the answer yes. Time, even as a subjective phenomenon, may be plural. May come in different flavors, different densities, different rhythms, depending on the organism living inside it. We have already noted that astronauts grow slightly taller in space, their spines decompressing in the absence of gravity's constant pressure. This is worth pausing on again in the context of time, because it exemplifies a broader truth. The body is not a fixed object moving through time and space. It is a process, continuously shaped by the physical conditions it finds itself in. Alter the conditions, remove gravity, change the pressure, change the temperature, and the body changes with them. The self that returns from 6 months on the International Space Station is not, in every physical respect, the same self that departed. It has been altered by the environment of space, bone density reduced, cardiovascular changes accumulated, the microbiome shifted, the spine temporarily elongated. We think of our bodies as stable containers for experience. They are actually dynamic physical systems that respond continuously and sometimes dramatically to their circumstances. And the day itself, that most fundamental unit of lived time, was once of very different length. We have visited this fact before, but it belongs here, in this more reflective context about the nature of time. In the early history of Earth, the planet was spinning much faster. Days were 6 hours long. The familiar rhythm of light and dark, the cycle that has organized life on Earth for billions of years, was running at a pace nearly 4 times faster than it does today. The day has been slowing, fraction by fraction, across geological time, braked by tidal friction, and it will continue to slow. The rhythm that feels most natural, most built into the body, the 24-hour cycle of waking and sleeping, of light and dark, is not a physical constant. It is a current value in a changing quantity. Life adapted to the day length as it was at each stage of evolution, and will continue to adapt as the day continues, imperceptibly, to lengthen. Time itself changes across history. Not in the sense of speeding up or slowing down, the laws of physics are, as far as we know, constant, but in the sense that the physical cycles that give time its experienced texture, its felt rhythm, are themselves subject to change. The year is stable. The day is not. The second, defined now by atomic transitions, is held fixed by definition. But the natural periods that shaped how life experiences time, these have changed, are changing, will change. And we have already established, in an earlier part of this journey, that every observation is slightly delayed. Light takes time to travel. Sound takes time to cross a room. The neural processing of sensation takes additional time. The moment you experience is never the moment that is happening. It is the moment that was happening, a small fraction of a second ago, reassembled by a brain that has learned to present it as now. We live, always, in a slightly constructed present, a present built from signals that have already passed, smoothed and synchronized and edited by a nervous system too sophisticated and too fast for us to perceive the editing as it happens. The now is real. but the way we access it is always, slightly, through the past. All of this, the 1/3 of life and sleep, the ancient shark, the changing length of the day, the delayed present, suggests that time is not the simple, uniform, neutral container for events that ordinary experience implies. It is multiple. It is variable. It is experienced differently by different organisms at different metabolic rates, in different gravitational fields, at different velocities. It changes over geological and cosmological scales. It is, at the quantum level, perhaps not fundamental at all. Some approaches to quantum gravity suggest that time may be emergent, arising from deeper timeless relationships, rather than being a basic feature of the universe from which everything else follows. What time is, ultimately, remains one of the deepest and most genuinely open questions in physics and philosophy. Not a solved problem waiting to be popularized. An actual open question, about which serious people disagree in fundamental ways. And so we arrive, at last, at the place this entire journey has been circling. The question of what reality is has been asked, in various forms, across every section of this exploration. And now, at the end, it is worth sitting with the answers that have been proposed, not as competing claims where one must win, but as different lenses, each illuminating something the others don't. The first and most familiar view is that reality is fundamentally physical. Matter and energy, obeying laws, constituting everything that exists. In this view, consciousness, experience, information, all of these are real, but they are real as properties or products of physical systems. The universe is made of stuff, and all other things arise from the behavior of that stuff. This view has powered the greatest scientific achievements in human history, and it remains the working assumption of most practicing scientists. The second view holds that consciousness is not derived from matter but is more fundamental than it. That experience, awareness, the quality of being on the inside of a life, this is the primary fact, and the physical world we describe is, in some sense, an object of experience rather than its source. This is not a mystical claim in any simple sense. It is a serious philosophical position, held by serious thinkers, motivated by the hard problem of consciousness, the fact that no physical account of the brain has yet explained why any of it feels like anything from the inside. The third view says the deepest layer is neither matter nor mind but information. Pure mathematical structure. The physical world and the experiencing mind are both modes of something more abstract, a computational or informational substrate from which both matter and consciousness emerge. In this view, asking whether the universe is physical or mental may be like asking whether a message is the paper it's written on or the meaning it carries. The answer is that it is the message, the structure, the pattern, the information, and the substrate is secondary. The simulation hypothesis sits within this third territory, in a sense. If reality is fundamentally informational or computational, the distinction between a universe that is running on some physical substrate and one that is running on a computational substrate becomes less absolute. We cannot, as has been noted, rule out the possibility that what we experience as physical reality is a constructed simulation. We have no experiment that settles the question. The reasons to think it unlikely are largely intuitive, and intuition, as this entire journey has demonstrated, is not a reliable guide at the edges of what is known. Panpsychism offers a different kind of bridge, not between matter and simulation, but between matter and mind. The proposal that consciousness or proto-conscious properties are distributed throughout nature, present in some form at every level of physical organization, dissolves the hard problem by dissolving the sharp boundary between the mental and the physical. If experience is woven into the fabric of reality at the most basic level, then the emergence of human consciousness from brain activity is not a miraculous exception but an amplification of something that was always present. And perhaps the most honest conclusion, the one that neither claims more than can be justified nor retreats into comfortable agnosticism, is that multiple perspectives are genuinely necessary. Not as a diplomatic compromise between competing views, but as a reflection of the fact that reality, whatever it is, presents itself differently at different scales and in different modes of inquiry. The physicist studying quantum fields and the philosopher studying consciousness and the ecologist studying forest networks are not all describing the same thing from different angles. They are each in contact with real features of existence that are not fully reducible to what the others study. The universe is structured in layers, and each layer has properties that require their own appropriate mode of understanding. Scientific models are always provisional. This is not a weakness of science. It is its defining strength. Every model in the history of science has been an improvement on what came before, and every model currently accepted will be refined, extended, and in some areas replaced by what comes after. Newton's mechanics was not wrong, it was a limiting case of a deeper theory. The same will be true of theories we currently hold. The provisionality is not relativism. It is the engine of progress. Science does not claim to have reached the final account. It claims to be moving towards something with more accuracy and less error than what came before, by a method designed specifically to self-correct. The history of ideas about reality is a history of successive surprises, each generation discovering that the previous one's certainties were approximations, and that the universe is stranger, richer, more complex than anyone had previously had reason to suppose. There is no indication that this history is over. There is every indication that it continues. Reality remains unfinished. Not unfinished in the sense of being incomplete or waiting for a final piece to fall into place. Unfinished in the sense of being genuinely open to new questions, new observations, new frameworks, new ways of thinking that haven't been invented yet. The territory of what is real keeps expanding as understanding deepens, and the expansion does not appear to be approaching a boundary. This is the place where physics meets philosophy, where neuroscience meets metaphysics, where the practical and the contemplative become, briefly, the same thing. The nature of reality is not a question with an answer at the back of a book. It is a living inquiry, one that each generation inherits in a richer form than the one before, and passes on richer still. And it belongs to you. Not to specialists, not to experts, not to those with the right credentials or the right framework. The question of what is real is the most universal question there is, and every conscious creature that has ever looked up at a sky or wondered about the nature of its own experience has been, in some sense, participating in the same inquiry. You have spent this time moving through the layers of it, From the everyday assumption that the world is solid and stable, through the quantum fuzziness beneath matter, through the strange geometry of space and time, through the hidden networks in forest soil and the biophoton glow of living skin, through paradoxes and philosophical debates and cosmological mysteries, all the way to here. Here, where the questions are still open, where the wonder is still intact, where the universe, in all its strangeness and all its generosity with mystery, continues to be exactly as extraordinary as it has always been, whether or not anyone is awake to notice. And now, perhaps, it is time to stop noticing for a while. To let the questions settle. To let the mind go quiet and the body go still, in whatever comfortable dark you have found yourself in this small corner of a universe that no one yet fully understands. The stars are doing what they always do. The earth is turning, slowly, as it always turns. The quantum fields are humming beneath everything, as they always hum. And somewhere in the deep ocean, a shark that was alive before modern science existed moves through the dark water with the unhurried patience of a creature that has never needed to know what it is. Rest now. The mystery will still be here in the morning, patient and vast and entirely yours.